Thanks so much for joining this symposium. This has been obviously a year and a half in preparation, and then we had this funny pandemic thing hit in the middle. So I'm glad to see this finally be realized. If only in a virtual space, but I think we have a couple really good talks lined up, and I'm really looking forward to hearing them and learning a lot about Opacity. Just a general kind of information about the schedule. The schedule is available on the symposium website. Hannes, maybe you can type it into the chat. The schedule is, oh, he's also, there we go. The schedule is available on this link. It's also copied here on the slide that you see now. Since we moved to the online format and changed the date, we had one person drop out, which opened up one slot. So Hannes and I decided we would take this as an opportunity to introduce the general topics, themes, and questions of the symposium, and maybe already set some groundwork for some of the future talks in the symposium. So I would say, without much further ado, we'll just get started with that. The talks are in keeping with the AISB schedule. The talks have a total slot of 25 minutes. The speakers are free to use those 25 minutes as they see fit. So if you want to talk for 24 minutes and have 1 minute of question, that's fine. If you want to talk for 15 and have 10 minutes of questions, that's fine too. So two talks of 25 minutes per hour, that leaves 10 minutes at the end of every hour or just before the full hour. Those are going to be short breaks of 10 minutes each for you to get more coffee, go to the bathroom or something like that. But we'll try otherwise to keep to the schedule fairly strictly, also so that people can switch between symposia and so on and so forth. Are there any questions, just to make sure? If there are any questions, the best is probably to put them into the chat, at least while somebody is speaking. Also because then, like, I cannot see everybody's screen at the same time. I cannot see if people are raising their hand or something. So if you have a question, put it in the chat. In the Q&A, I'll try to, well, Hannes and I will try to identify people who are asking something. Okay, yeah. Yeah, Katie, we haven't started yet with the presentation, so we're only showing the first slide right now.
Oh, sorry.
All good. Hi, Katie. Okay, well then I would say I'll begin. Overcoming opacity in machine learning is the topic of this symposium, right? With especially focus on this concept of opacity, which has of course become very present and important in the context of machine learning, and leading towards this kind of great promising research area, which some people like to call interpretable or explainable AI. Hannes, you want to move on, please? Yeah. So just to identify some of the key themes of the symposium, right? I suppose this is going to be familiar to most people here, but just in case, right? We know that AI is kind of increasingly important in many different domains and sectors of society. And one of the big drivers of this kind of new boom in AI is, of course, machine learning, just as one approach to developing AI systems. As it happens, it turns out that many systems developed using machine learning are what we call opaque. This has given rise to the black box problem, which is discussed also in non-academic circles in the media. People compare current AI systems to black boxes. One of the aims of this symposium is to be clear and to maybe come up with a definition of what exactly opacity is. What exactly is the problem that we're facing? What we know, however, or what seems to be the case, is that this problem, this caused by opacity, has practical consequences, it has theoretical consequences, and it has ethical consequences. So opacity seems to be an obstacle to the responsible use of AI. It might not be fair or appropriate to have end users interact with opaque systems. It also has practical challenges, for example, for developers, some of which we will look at in a minute in this first presentation. Then anywhere where there's a problem, then computer scientists, of course, immediately start thinking about possible technical solutions. And so these technical solutions are becoming increasingly important and also prevalent. So often these are known as solutions coming from explainable AI or interpretable AI. And the key idea of these technical solutions, which we'll look at much more closely over the course of this symposium, is what kind of solutions are there? What can they actually do? What can they not do? What are the limits of these technical solutions? So can opacity be overcome? Hannes? So just to identify some kind of key questions for discussion in this symposium, and these are going to be questions that I'm going to raise here in this talk, and Hannes is going to raise too. But also these questions are going to be raised in much more detail over the course of the symposium as a whole. The first key question, which I think cannot be neglected, especially for the more philosophically inclined in the audience, is to find a definition of opacity, right? So philosophers like to define the concepts they work with. That's almost well, it's part of their job description. So can we define opacity and therefore really understand what the black box problem actually is? Are there also different types of opacity? Several talks today will be looking at different kinds of opacity and distinguishing between different kinds of opacity. Some of these distinctions are already in the literature, others are new. And then, of course, also, what are the sources of opacity, right? So we say that opacity comes because of machine learning, but why exactly? Once we know what opacity is, then I think it's worth asking questions about the effects of opacity. Who or what is affected by opacity and how exactly, right? In which context does opacity arise, and who are the stakeholders that maybe face problems because of opacity? Here in particular, it's worth distinguishing between ethical challenges, epistemic challenges, so challenges to do with knowledge, and engineering challenges, very practical things that interest mostly developers. And then, of course, once we have a problem, how, if at all, can and should opacity be overcome? I like to distinguish here between the normative question about should and the descriptive question about can, right? The normative question is basically the question, can we specify relevant norms and standards for explainable AI? Can we say, well, what should be done in order to overcome opacity? And then, of course, do we have technical solutions that can satisfy these norms and standards? I'll now pass on to Hannes, who will be talking in particular about opacity, what opacity is, and the first effects of opacity, which will lay a nice groundwork for the talks to come. All right, go Hannes.
Yes, thank you, Carlos, for this kind introduction. And in order to not waste any more time, I will directly tackle the first question, namely, what is opacity? And I think that one of the first things that we notice when we have a look at the huge amount of literature on the black box problem or opacity is that terms like yes, opacity or non-transparency, terms like non-interpretability, or the good old black box have no formal or technical meaning yet. And I think that is a point that cannot be stressed enough, but is in fact too rarely stressed in the literature. So terms like opacity or black boxness are, I think, highly metaphorical notions that suggest that it is somehow difficult to look inside a system. It is difficult to look into the box. And well, why is it difficult to look into the box? Because it's black, right? And this is a problem because looking inside a system often helps us to answer questions that are very important and that are and that we are interested in, namely about why a system does what it does and how it works. The problem now is that opacity somehow prevents us from answering these questions. And since we want to answer these kind of questions, it is important to have a very clear and a very precise understanding of concepts like opacity. Here, precision is needed both to know what the problem is and also to identify then a possible solution to it. And this is why we try to shed some light on the concept of opacity. And we think that a good starting point for this is the perhaps first and the perhaps most influential analysis of opacity, which goes back to Paul Humphreys. Now, although his work originally is primarily concerned with computer simulations in scientific disciplines such as high energy physics and molecular biology, it turns out that his analysis of opacity can be made fruitful for discussions concerning the opacity of machine learning systems in AI as well. So what does he say? He says that a process is epistemically opaque relative to a cognitive agent X at time t, just in case X does not know at t all of the epistemically relevant elements of the process. In his paper, Solving the Black Box Problem, Carlos then emphasizes that there are at least two features worth highlighting here. The first one is that opacity is agent relative, which means that a machine learning system or computer system is never opaque in and of itself, but opaque only with respect to some particular agent or stakeholder. Yes, all these different agents have different knowledge, they have different abilities, and of course, they ask different questions when they want to understand a machine learning system. And the second important feature is that opacity is an epistemic property, which means that it concerns the lack of a certain kind of knowledge. And according to Humphreys, this knowledge is knowledge of the system's epistemically relevant elements. Now, Humphreys does not further analyze this notion of epistemically relevant elements. Fortunately, Carlos does in his paper, and he gives us some examples for epistemically relevant elements. The first ones are reasons for acting in a particular way. So say we have a loan risk assessment system and you ask yourself why it won't grant you a loan or give you a loan. The answer to this could be the reason that your income is just too low. Another epistemically relevant element could be internal or external causes of a system's particular behavior, like specific pixel or pixel regions in the input data, which are most responsible for a particular classification from a machine learning classifier. And last but not least, another epistemically relevant element could be the computational or mathematical structures that determine the system's behavior, like the features or learned representations that help the machine learning system to classify cats or dogs, right? And all these epistemically relevant elements can then be cited by an agent to explain the occurrence of some other element or of the system's overall behavior. Now, to wrap Humphreys and Carlos's ideas up and answer, or at least give a working definition of what opacity is, that is, of course, open to discussion. We would say that opacity is a particular agent's lack of knowledge of the reasons, causes, and mathematical or computational determinants of the system's behavior. So now that we know what opacity is, the symposium is over. No, now that we know what opacity is, the next question then might be what gives rise to this kind of opacity. Fortunately, Jenna Burrell identifies three sources of opacity. The first type of opacity is opacity as an intentional corporate or state secrecy, which is a form of proprietary protection and which is also a largely intentional form of self-protection of companies, for example, who wants to protect trade secrets or competitive advantages, but sometimes also to conceal sidestep regulations, to conceal the manipulation of consumers or patterns of discriminations. Say we have, for example, a network security application of machine learning that deals with spam, scam, fraud. These kind of systems may need to remain opaque to be effective in a game of cat and mouse with all these spammers and scammers out there, right? And a very obvious solution to this type of opacity as intentional secrecy, is to just use open source software as an alternative to these proprietary algorithms, or just make the code available for scrutiny through regulatory means if necessary. The second type of opacity then is technical literacy. And this type of opacity stems from the acknowledgement that, at least at present, writing and reading code and the design of algorithms is a specialized skill, and these skills are or remain inaccessible to the majority of the population. Also, good code, according to Burrell, does double duty, which means that it must be interpretable to humans, but not only to humans, also to computational devices, and they have completely different demands on what exactly what it exactly means that it is interpretable. And to mastering this act of balance is not easy, and the only solution to this is then widespread educational efforts to increase the technical literacy in the population. Yes, and the third type of opacity is opacity that arises because of the complexity of machine learning systems. I won't say much about that because I think we will hear about this a lot today. So just so much that it stems from the mismatch from the mathematical optimization and high dimensionality characteristics of machine learning and the demands of human scale reasoning and styles of semantic interpretations, but also of the complex interplay of the learning environment, the systems architecture, and the learning algorithms. So complexity, I think, is what we want to talk about when we talk about opacity today. So now that we know what opacity is and what are possible sources for opacity, we might ask who is affected by opacity. And Tomset et al. Provide us a helpful taxonomy of stakeholders in their so-called machine learning ecosystem. That is, stakeholders who depend on or interact with a computing system that is programmed using machine learning here. And all these different stakeholders have different kinds of knowledge, they have different kinds of abilities, and they play different roles in the machine learning ecosystem. We have the machine learning system here, which is created by the creators, trained on the data from the data subjects. The trained model is then provided with input from the decision subjects, and the operators also have access or direct access to the system's outputs. And the executors make decisions informed by the machine learning systems, which directly affect the decision subject. And also we have the examiners here, which then assess the fairness of the decisions, probably according to laws or regulations. Now, each and every one of these different stakeholders is affected in his own unique way. For example, if we have the decision subject, they probably, if they have to work with an opaque system, cannot understand how their data is used and how decisions are made if they do not know the patterns of reasoning behind it. We have the examiners who cannot assess the fairness of decisions and who do not know the reasons for a system's output, and the creators who cannot develop or debug systems because they don't understand it. So this is not everyone who is affected by opacity, but just one of the first. Okay, I've read it. So I stopped at that point with who is affected by opacity, and just say something on further contributions in the symposium. We will hear about who is affected by opacity by Juli Schwer, Paul Grünke, and Raffaella Hillebrand, who tell us something about the effects of opacity in scientific research, by André Paes, who tells us something about the role of opacity in human-robot interaction, or Vincent Müller, who tells us something about different types of opacity and their effect on data privacy. So sorry for talking so long. Carlos, it's your turn. How, if at all, can and should opacity be overcome?
Right, so if we know what opacity is and also who is affected by opacity and where it's coming from, then it's good to also look briefly at the other side and recent attempts to overcome opacity. And the typical response here, as most of the people attending the symposium will probably know, is that there's a big trend now toward explaining the behavior of opaque systems, or interpreting or understanding the behavior of these systems. And just like opacity, these terms, explanation, interpretation, understanding, is not helpful if the meanings of those terms are not clear. So, and in particular, several authors, Zach Lipton, first and foremost, perhaps, right, has stressed the fact that these terms are in fact not very clear, and that it's important to make them clear before we can proceed. Mach mal weiter. Yep. So one way in which people have sought to clarify these terms and define explanation, understanding, and interpretation, right, is through developing theoretical frameworks. Now, there's many different theoretical frameworks that have been deployed in this context, also adopting different perspectives. So just to mention some of them, Zerilli and I'll come up with a framework from especially Dennett's work on intentional systems, right? Saying that explanations can be understood as like different kind of stances in Dennett's framework. I, in my own paper, have looked at how we might define these terms from a cognitive science perspective, trying to distinguish in each case between explanation, understanding, and interpretation. And perhaps most recently, Erasmus et al. Adopt a philosophy of science perspective where they look at different explanatory frameworks, let's say from physics or biology, right, and try to understand to what extent we might use these different types of explanations to explain the behavior of opaque systems, and in each case saying what the difference is between explanation, interpretation, and understanding. The key idea here is in deploying these frameworks is that we can define norms or standards. So basically goals to strive toward when doing explainable AI. When trying to overcome opacity, these kind of frameworks help us know what we should actually be doing. Should we be looking for some intentional stance story? Should we be looking at some algorithmic level analysis? Should we be looking at a mechanistic explanation? What exactly should we be doing when we do explainable AI? Hannes? We'll also have some talks that will look a little more and try to more carefully specify some of these norms and standards, right? We'll have Katie Creel that looks at one particular measure or thing that has been important is user satisfaction, and trying to show that user satisfaction might not in itself be a good measure of explanation quality. We'll also have David Watson, who will look at statistical analysis and the importance of certain kinds of statistics when giving an explanation, in particular that explanations should always be accompanied by some measure of the uncertainty in the explanation. So once we specify norms, so how should opacity be overcome, then it's worth looking at how we might actually overcome opacity. How can opacity be overcome? And here's, of course, where explainable AI comes in. This is so a screenshot from a slide set that probably everybody who's worked on opacity has encountered by David Gunning, where I think the term explainable AI is coined for the first time. The idea here is to somehow either change the machine learning process, right, or have some kind of explanation interface, right, that somehow tells the user how a system works or why it is working as it does, right? And the development of these machine learning methods or the development of these explanation interfaces is kind of what explainable AI is all about. Go on, Hannes. So, and here I think it's worth making two distinctions in particular, because in this symposium we'll look at one in particular. On the one hand, some people in explainable AI try to evade the black box problem by developing what one might call interpretable systems that are not opaque from the beginning. And then others are interested in solving the black box problem through what we call post hoc explanation methods. And in each case, you would want to ask the question, okay, to what extent have we satisfied the norms and standards developed in these theoretical frameworks? In today's symposium, most of the talks that will work on technical solutions will in particular look at post hoc explanation methods. Hannes? And in particular, we'll have Lok Chan look at this question of representational accuracy, to what extent a post hoc explanation needs to faithfully depict the internal processes of a system. And we'll have Richard Tomset discuss some technical barriers to maybe think that post hoc explanation is not always going to be as successful as we want. So, and that reaches now the end of this brief introduction. We ran on just a minute long. So I would say, just without further ado, here again is a reminder of the program for today. We also don't forget to look at the symposium website if you want to look at this in a bit more detail. But we'll first have a talk by Katie Creel on function and user satisfaction in explainable AI. And maybe while Katie sets up, we have time for just one or two very brief questions. Thanks a lot for listening. If there's no questions, that's fine too. Then I would say let's move on to Katie, but let's just wait a minute. If somebody has a question, I think it's most effective to put it in the chat. Or Paul, did you say something?
Yeah, thanks. I wasn't sure what's the best method. So I was wondering about the definition that you gave by Humphreys. So in this definition, he speaks of a process, right? And then you kind of switch to computer systems. And this is not strictly speaking a process. So I was wondering whether you thought, what you thought about this switch of ontology, basically.
Good. Yeah, that's a fair question. Honestly, no, I haven't paid too much attention to it. I know that I'm doing a switch here. I like to talk about systems, and Humphreys likes to talk about process. But I mean, perhaps so a process is, in my understanding, it's kind of something that a system might exhibit over time. It's more something functional, whereas a system might also include the physical stuff, if you will. And to me, I mean, at least certain kinds of stakeholders are also interested in the physical hardware. So I generally like to talk about systems, but I think most of the things that we talk about under the guise of opacity would also apply just if you talk about processes. But there's surely some room here to try to argue, well, maybe process or system, maybe opacity affects one more than the other. I haven't thought about it too much. Thanks, Paul. Well, then I would say let's move on to Katie, also in the attempt to stick to the AISB schedule. Katie, you ready? Good to see you.
Hi. I know it's afternoon for most of you, but it's morning for me, so good morning.
Good morning.
Just briefly on that discussion, I have a paper that talks a bit about transparency and the Humphreys framework and does talk about the process ontology distinction, so I'll just put it in the chat.
Oh, great.
Okay, so meanwhile, I am giving a somewhat different presentation. Okay, screen sharing works, good.
Yep.
So, all right. Function and user satisfaction and explainable AI. So this is a paper that I wanted to write because I noticed a trend in terms of which kinds of solutions people were gravitating towards in more sort of like industry-driven contexts. And so I wanted to sort of like provide a philosophical perspective, and I would love to hear all of your thoughts about how to better frame this and what I think is a worrying trend, but we'll see if you agree. Okay, so we have this fundamental problem, which is that in order for an automated decision-making system or any kind of decision aid to be useful, it has to be used. But we know that in practice, opaque or black box automated decision-making systems are often ignored. And this is a very old problem. So I found, a bunch of papers from the 50s and 60s about, punch cards as tools in differential diagnosis. As long as we've had sort of like decision aids, whether on paper or with punch card systems to help doctors go through sort of logical workflows of various kinds. People have been trying to use these decision aids to improve diagnostic success. But these sorts of decision aids are quite transparent. You have a sense of why the diagnostic workflow is set up in the way it is, and you can often go back and figure out why each recommendation is made. And that's not always the case for explainable AI for expert users. So in a well-known paper that presents a model called LIME, there's this hope that we would have the model, we would have our data and predictions, and then we would have this outside explainer, which in their case is LIME, that would fit a local model to the decision space just around the token decision that's been made and say, okay, let's probe the decision space, let's vary the parameters, let's say, oh, if the patient had come in without fatigue, what would the diagnosis have been according to this model? If the patient had come in sneezing or not sneezing, if they had been 64 instead of 65, let's use. All right.
Yep, perfect.
Right, explainable AI for expert users. So there's, I think, an important difference between these two different possible framings of what the problem of explainable AI for expert users is. One is how to increase trust in automated decision makings such that doctors and other professionals will rely on them in decision making. And that's the framing that's often adopted in more sort of machine learning or computer science-based literature is the framework of what do we need to do in order that people will trust it. But I want to propose that what we need to be doing instead is ensuring appropriate trust in automated systems so that professionals use them while understanding their limitations and so that they understand how to calibrate the level and degree of trust appropriately. So we shouldn't just be trying to increase net total amount of trust without a window into how they, as epistemic agents, can calibrate their trust better. So there's been an idea for a while to create a benchmark. And this makes sense because benchmark has been a useful strategy in a lot of contexts. But then there's a question of what should it measure? So in ImageNet and other classification performance tasks, even though we know that a lot of these benchmark tests are flawed in certain ways, like the labels themselves are wrong, there's at least a clear sense of, well, the task we want people to achieve is labeling the images, and if they can do that, then they've succeeded at the benchmark test. But a benchmark test for explanation is a bit conceptually trickier. So there's a well-cited paper by Doshi, and Kim in which they propose that a benchmark test for explanation should test user satisfaction. So the idea here is let's provide an explanation that a target audience for a task finds satisfying or useful. And what we're going to do is we're going to have human subject trials and measure the automatically generated explanations versus human provided explanations. And the hope is that for each task, we could do this sort of more fine-grained benchmark, but if we can't, maybe we just improve interpretability by using these benchmark tests to set up a more generic ranking of the interpretability of models. We're going to say, in general, this model is more interpretable than that model. And so if you had to choose, this is the one you should choose if you can't run your own benchmark tests. So what would these tests look like? Well, the most common one, both in this paper and in other papers, is this idea of binary forced choice. So humans are presented with pairs of explanation and they choose the better one. Sometimes there's also more sophisticated ones, like maybe you have an explanation and you have an input, and then you have to simulate what the model's output will be. Or maybe you have an explanation, an input, and an output, and are asked to figure out what has to be changed to change the prediction to a desired output. So what I think is interesting here is that user preference is the criterion of evaluation. And so there isn't room in the account for distinguishing between a feeling of understanding and a true explanation. I also think it's worrying that the classes of models, there's this sort of plan B that the classes of models are ranked by interpretability. I don't think this is going to work because there's too much interclass variability in how interpretable certain models are. And I'm also concerned that many strategies such as text explanation or visualization may be well ranked, but are explicitly simplifying or inaccurate in certain ways. So first concern, and I think this is the most important one, if user preference is the criterion of evaluation, then we can't pull apart understanding and true explanation. So why is this a problem? Well, what we're going to measure in benchmark tests, the reason that they're powerful is that what we measure is what we optimize. And so if we optimize for the feeling of understanding, then we are guaranteeing the conditions to set up a potentially systematically misleading but prima facie plausible explanation. And I think in particular, this leads to an over-reliance on visualization, because we know that people always rank visual explanations as being more satisfying than text-based explanations. But this isn't to say that visual explanations are always bad, but I think it might skew the results in terms of what is actually providing, explanations that are good in other ways, such as being accurate or being actionable. And I think the concepts of idealization and abstraction are important here, because yes, they are valuable in creating cognitively tractable explanations, but without access to information about the true functioning of the systems, the users don't have a way to determine whether anything about the explanations in the two binary choice scenarios are true. And so without this, it's impossible for the users to know whether their trust is warranted or whether this feeling of satisfaction that they have is tracking anything. Okay, so that's concern number one. Concern number two is about the idea that we can rank classes of models. So if we say that all decision trees are more explainable than all neural nets, we're sort of committing ourselves to the idea that, a multi-thousand leaf decision tree where each of the leaves is this, tiny GRU-like factor is more explainable than a very small, very easily traceable neural net. And so I think this is just a super quick illustration of the fact that I don't think it's possible to do rankings on this broad brush. There's too much interclass variability. And also, as Carlos was saying earlier, this idea of ranking presupposes a goal agnostic or model independent explanation, but explanation is goal relative. So given that we might have different goals, we can't set up a unique metric of explanation without knowing people's goals. Okay, third concern is that visualization always boosts satisfaction scores. But this means it prioritizes local explanations like Lyme, and it's often very fragile to minor perturbations in the input that don't actually matter in terms of the functioning of the system. And there's this interesting potential for circular explanation that I think has been underexplored. So let's say I'm trying to explain which parts of an image a neural net classifier found particularly salient. So salience explanations are very common. And so I say, okay, the original image, which is obviously crazy, is an electric guitar, it's maybe an acoustic guitar, and it's a Labrador. Sure, so I can sort of tell a just-so story about why the pieces picked out contributed to those labels. But we know that salience is very fragile. So for example, when we change a background, like putting this blue checker pattern behind the standard digit recognition task, we notice that the salience itself changes. So instead of being this nice picking out of the 7 itself, we get these much more muddied pictures. But interestingly, the performance does not change. So the salience explanation is no longer as visually appealing, even though our performance at recognizing the digits hasn't significantly changed. So things like this, I think, should make us a little bit worried about the extent to which salience explanations are tracking what it is that's actually happening to cause the outcome of the successful classification. Okay, so if salience in this case is failing to provide an explanation, so on what accounts of explanation is it doing that? And how would user understanding account for the difference between these two cases? So this idea of distinguishing explanation and the feeling of understanding is relevant for the design of human subject experiments, because in a lot of cases, people are trying to add nuance by saying, okay, if we're designing a system for doctors, we need to have doctors be the ones in the tests. Fine. But subject expertise is not enough for evaluation because you also need information about the case itself. And I think this is especially important for scientific explanation. So what do? I'm not totally giving up on benchmark user tests. I think they're still possible, but we need to make them either factive or functional. So we need to either say, okay, given that the system in fact functions in this way, which of these texts or images is the most explanatory? Or we need to change the measure to being a much more functional standard that says, if you are trying to perform a task, how much does the explanation improve your performance? So how much does knowing this from one of these explanatory measures help you do something that we can measure your performance on? All right, so thank you very much, and thanks for being patient with my tech issues. I would love to hear your questions.
Cool, yeah, thank you, Katie. Yeah, this was really interesting and connects with, I think, many talks that we have yet to see today. If somebody has a question, I would say we are a small enough group that you can just speak up, or if you prefer, write the question in the chat. Anyone? We have a question in the chat from Andres. I'll read it. What do you mean by a true or factive explanation, considering that there is no access to the true function of the system?
Yeah, that's a great question. So I was imagining cases in which, because we are running these tests, we do have access to the functioning of the system. So we can design a system that maybe is small, or maybe we can trace, or we built so we have access to various relevant features of it. And so this might not work at the factive approach might not work as well if we're trying to provide an explainer for something that we don't have the relevant kind of access to. But in that case, I think that would be the time to switch to the more functional approach.
Okay. Any other questions? Oh,
I have a question. Can I? Thanks, Katie. I really like the talk. I'm also really worried that this kind of work is sort of just training these systems to be rhetorically effective rather than so you get to making great bullshit artists rather than actually providing like explanations. But I'm wondering, like, what I really want an explanation to do is give the user an understanding of how the system works. But if that understanding is like good enough, then in some sense the system is no longer necessary. So because they could sort of perfectly approximate it themselves. So can you help me not toggle between these two thoughts?
Yeah, that's really interesting. So yeah, I would love to hear your follow-up on this. I could imagine a case where we wouldn't toggle between them in the same sense that we wouldn't in, let's say, like the old automated proof solving literature, right? So I might have a pretty good sense of what it is that my proof solver is doing as it's cranking through these thousands of cases, but I couldn't, hold it all in my mind or have this more subjective feeling of understanding it. So I think in a lot of cases where the issue just is the sheer size or scope, there might be a sense in which I can understand what it's doing well enough to trust it, while still not being able to follow every decision-making process well enough to replicate it myself. Does that seem right?
Yeah, I agree with you. I guess that is right. It's like understanding what it's doing has to somehow fall short of being able to simulate it yourself. But with a neural net, like, I just don't like having some kind of high level I don't know what that would look like. What is like a high level understanding of what a neural net is doing, short of being able to implement it myself in my own hardware. But yeah, that's a hard question. So I don't know if you have thoughts, like I'd be interested to hear them.
Yeah, yeah.
If I could jump in maybe just for a second. First of all, thanks a lot, Katie, for that really nice talk. Also, hi, Casey, long time no see. But maybe part of the answer to the question is kind of going back to that distinction between local and global, right? Like it could be that some incredibly fancy function behaves quite nearly linearly in a certain region. And in that case, something like Lime or SHAP may be able to give you a pretty good answer for you. Maybe it is true for you that, you know, there is this like very nice kind of monotonic relationship between some input feature and the output. And that doesn't let you simulate generally from like the whole feature space, but it could let you make decent approximations of how that function will perform on someone similar to you, if they are sufficiently similar along the relevant features or something. And I think that kind of lesser goal is kind of characteristic of local explanations, right? It's not trying to give you the full regression surface. It's just trying to say, right around here, it behaves kind of sort of like this.
Yeah, absolutely. And I do think that can be valuable. I think my worry about the local explanation in general is that it doesn't give the person, the explainee, the capacity to know, you know, what are the cases in which what I really wanted to know was why I was shunted to this part of feature space at all. So there might be cases, I mean, I think the most obvious case, but by no means the only case, is, you know, if let's say I'm in an automated decision-making system and I'm a decision subject, and it turns out that the race of the decision subject is going to put them in one part of the feature space or another. And then, you know, the explanation I might get from the local explanation would be like, oh, well, if you'd had a slightly higher income, then in that case, you would have gotten the loan. But actually, I would really have loved to know that if I had been, you know, in a different zip code or in a different racial group, in fact, that would not have been the relevant criterion at all. And so that's my worry with those types of local explanations. But I agree with you. I think, you know, they are understandable in that sense. It's just, how can we make sure people get both?
I would say let's take the time for one more question, since we had those tech issues in the middle. Anyone? If not, I'll ask a quick question. So I mean, I'm inclined to agree fully that of course user satisfaction is not sufficient, and we want something like true explanation. But just to play devil's advocate here, so I often see this this distinction that philosophers like this true explanation, kind of this factivity, whereas like computer scientists, tech people, are for them it's enough to have this this user satisfaction. But what really is the problem with just having an explanation that is sufficient for user satisfaction? Like, does the user then, you know, is the user then not able to use the system or process as well, right? So I agree, in certain corner cases, it might not, you know, the explanation might not be sensible anymore if it's not factive or something like that. But for the most part, right, it seems that in just everyday interaction, lay people, all they need is user satisfaction in order to keep using the machine.
Yeah, I mean, I think that is like a perfectly constructed devil's advocacy for a position that is very much out there and that I very much disagree with, in the sense that I think it leads to a scenario where the interests of the people making the system, whatever it is, are prioritized over the ability of the people who are the decision subjects to contest the decision, to explore the decision, to, you know, do any of these sort of like longer time scale activities with the decision that aren't just like accept or reject it in the exact moment they hear it. And I think there's an interesting division within the more sort of computational community itself, right? Because I think what you just said is an opinion that's in some parts of human-computer interaction. But then there's this weird thing where a lot of machine learning people will talk about like ground truth. What is ground truth? I would love to know. But there's this sense that we can appeal to, you know, ground truth as a way to bottom line some of our decision systems or explainers that is valuable. But yeah, thanks for giving me the extra time, and sorry again for tech issues.
Yeah, it's no problem. Yeah, no, thanks a lot, Katie. I would say, right, exactly. Konstantin is doing it right. So then I would say, let's take a very short break of 5 minutes until, well, the full hour, wherever that is for you. Yeah, see you then. Hannes?
Oh, we can see your office from the outside.
Exactly, it's the small windows on the top.
Okay, so I think, yes, first of all, thank you for the great start. I hope you all make good use of this short break. And I think we should now directly start with the presentation or the next speaker, namely Otto-von-Guericke, who will present work on the epistemic risks in machine learning. And yes, I think, Paul, I think it's your turn.
Yes, thank you, Hannes, and also thank you, Carlos, for organizing this symposium, and welcome to our talk, Beyond Opacity, Epistemic Risk in Machine Learning. As you can see, this is shared work with Julie, who is also here, and Rafaela Hillerbrand, who is the professor at ETAS, where we both work. And as you can also see in the title, we kind of interpreted the topic of this symposium slightly differently than most other speakers, I think, because we try to overcome opacity by looking at something somewhat different, namely epistemic risks. And I will tell you in this talk what epistemic risks are, why it might make sense to look at them in the context of machine learning. And if we have time in the end, then shortly I will also talk about how this epistemic risk perspective might benefit us when we think about machine learning and understanding. But let's first start with some typical question that people ask themselves when they think about epistemic problems in the context of machine learning. They wonder about how we can get trust in the results of machine learning systems, how we might get an explanation or justification of the results, and how we can learn something about the world or understand about the real world phenomena that shall be represented by these machine learning systems. And in all these cases, opacity has been identified as one, if not the central difficulty in answering these questions. And we think that this is partly because, as has already been introduced by Hannes and Carlos before, there is this black box metaphor that sort of prevails in at least most of the philosophical discussions around machine learning, that these machine learning systems look like this. You have a black box in the middle, the machine learning model, and then you put some data in and you get some output and you don't really know what's happening inside this black box. And now explainable AI tries to open this opaque box and sort of tries to understand what's happening inside. But that's not what we want to do. We rather want to shift the perspective a bit, not because we think it's not worthwhile to talk about opacity, but because this other perspective might also be helpful, and rather focus on the decisions that happen during the development processes of these black box models, since these machine learning models don't just come into being and then we have to deal with them, but rather we can also look at the practice of developing them and using them. So what we will do, as I just said, sort of try to shift from this opacity onto an epistemic risk perspective. And by doing so, we rather focus on the decisions during these development processes rather than the resulting opacity of the machine learning model. And what we will do concretely, we will, after I now in the next few minutes introduce epistemic risks in general, look at examples, or sort of a class of examples of machine learning systems that use electronic health record data to basically predict health developments of patients. We'll get into this in a minute. So once more, what is the motivation to use this epistemic risk perspective? We think that machine learning systems are developed and used for particular purposes, and we should sort of recognize this. And since this is the case, these development processes, they involve various decisions in order to reach their particular purposes, and these decisions always come with epistemic risks. And by shedding light on how these risks are involved in the development of the machine learning system, we might actually sorry, that's our proposal. We want to shed light on how these epistemic risks are actually involved in the development of the machine learning processes. And yeah, one could phrase this as a turn of practice, since we don't really want to put into the center of our investigation the resulting model, but rather the practice of producing this machine learning model, and then also the application of this machine learning model. What are epistemic risks? In our work, we there follow what Justin Biddle and Rebecca Kugler proposed. They defined epistemic risks as the risk of error or failure that can arise anywhere in knowledge productive practices. And they especially highlight that epistemic risks are not only inductive risks, which is mostly associated with epistemic risks, so the risk of falsely accepting or rejecting a hypothesis, but various other kinds of errors as well, such as, for example, the failure to use your knowledge practice for an unintended purpose or not the intended purpose. And we will get to see some other potential epistemic risks or epistemic errors in the next minutes. Biddle and Kugler, they mostly use this conception of epistemic risk to highlight the role of values in machine learning or in modeling in general, values in an ethical sense. But we think that this epistemic risk terminology can also be fruitful if we use it even more broadly, because this will allow us to focus on the decisions that are made during the development process of machine learning systems, which then come with epistemic risk, which might often have ethical implications later on, but not directly. So we want to sort of take one step before and look at the purely epistemic impacts at first. So let's go back to this picture of the black box model and see how the decisions during the development process, or some of these decisions during development process, come in. So we have a training phase, of course, and during this training phase, we have to decide what kinds of data we actually want to use, so define the data type. And then we have to decide how we want to prepare the data. So do we want to curate these in some specific way to maybe correct for known biases, or do we just take all the data that we get and use them in the training phase? Then we have to decide how we want to design our algorithm, what kind of architecture we want to use for the machine learning model. And we have to make a decision how the output should look like. Will it be just an answer to a yes/no question? Will we get some percentage number as an output? Do we want our machine learning model to provide some kind of explanation for the result or not? These are decisions about the model itself. And then, of course, maybe most importantly, we also have a target system out there. So we have some specific purpose in mind by developing the machine learning model. Usually we want to learn something about a target, some phenomena in the real world. And in order to make a good representation with the machine learning model of this target, we first have to define for ourselves what is actually the problem that we want to address with our machine learning model. How do we want to operationalize the concepts that are present in this target phenomenon? So to get this a bit more concrete, we now try to illustrate these or some of these decisions with the already named example. So we will look at machine learning systems in the area of medicine and sort of take not one specific example, but just in general, there are many machine learning systems that use different kinds of electronic health record data in order to make predictions about the health status of patients, future health status or current health status, just based on these data. What are electronic health records? They may contain things like the patient's medical history, test results that the patient made, some treatments they got, laboratory findings, and so on. And if we want to now create such a machine learning system based on these electronic health records, we will have to do lots of decisions in this development process. And we'll now look at some of these decisions and figure out what kind of epistemic risks might be associated with them. And we follow here a review that Gianfrancesco et al. Made about such machine learning systems that are based on electronic health record data. And maybe just sort of to set a stage of what are the problems that people face there. So we have to think about these type of data before we start building our system. And electronic health record data is very heterogeneous in quality. So if you come from a high socioeconomic, you are in the member of a high socioeconomic group, then typically your electronic health record will be very comprehensive. You have your fixed doctor which you go to whenever you have a problem. So they will set up your electronic health record. They will fill it with the same type of data every time. And the data will be very useful for this machine learning system. If you are, or members of lower economic social groups are more likely to go to different doctors. They will also go less often to doctors, only with more severe diseases. And so the data about the electronic health records of these patients are less comprehensive and also already kind of biased, because, for example, they will only have, or not only have, but more often than not have severe diseases, and they might be different in type, because different doctors are more likely to enter this data differently. So what do we now have to do sort of as a consequence of these things? We have to first think about, is electronic health record actually a good data type to choose? Because, as this short story now more or less anecdotally will prove to you, that different kind of patient groups will be differently represented in the resulting model if we just use all the electronic health record data without further considerations. We have to think about how to choose an appropriate sample size. If we have a large data set and then only a small number of data points are allocated to specific group members or specific diseases, say, then they will most likely not show up as prominently as they maybe should in the resulting model. And if we already know that beforehand, that we have an underrepresented group or parts that are underrepresented, then we have to think about how we might manage this problem by maybe overrepresenting them in our training data, or making two different models, or whatever other ideas we come up with. Similarly, if we know about implicit biases, we can, in the model building process, or later on in the application of the resulting system, react to this known epistemic risk. So what we want to take away from this slide is, one point is that we can see that these epistemic risks are present in the development process of machine learning systems at various points. And the other one is that once we know about epistemic risks, there's also the upside that we can then manage these risks by trying to balance known biases, either in the development process already by trying to get a less biased model, or later on in the application, if those who use the model know about the epistemic risk, they can balance it there. Okay, let me now spend 1 or 2 minutes on how this epistemic risk perspective might be useful in the debate about machine learning and understanding. So one of the questions in the beginning was, how can machine learning models provide understanding about a real world target? And Emily Sullivan wrote a paper about this question, understanding from machine learning models. And in this paper, she argued that epistemic opacity might not be the most relevant reason that prohibits understanding, but rather the level of link uncertainty. And this she defines by the extent to which the model fails to be empirically supported or adequately linked to the target phenomenon. And in her paper, she also has some reference to a medical case, and she writes there, we want some indication that the model is picking out the real difference makers for identifying a given disease and not proxies, general rules of thumb, or artifacts within a particular data set. So how can the epistemic risk perspective be helpful here? Let's come back to this picture for one last time. The link uncertainty, that's the error between the machine learning model and the target. And if we want to assess this link, or the certainty or uncertainty of this link, then it makes sense to ask what could have gone wrong in the whole process. And if we know about epistemic risks and potential sources of epistemic risk, then this might be a very good start to assessing the link uncertainty between target and model. So let me conclude. We use this epistemic risk perspective in order to focus on the fact that machine learning systems are products of decision making and not just opaque artifacts that just pop up in the world. That there are certain kinds of epistemic errors that may be unavoidable is something that we see automatically if we take this epistemic risk perspective. But using this, we can also then manage and potentially balance these the resulting risks. And as a last point, epistemic risk can also be helpful to assess the level of link uncertainty and thereby add to the discussion about machine learning and understanding. Thank you, and looking forward to a discussion.
Yes, thank you, Paul, for shifting the perspective from opacity to all these epistemic risks associated with the development process of machine learning models. I think we are perfectly in time and have at least room for 2 or 3 questions. So just speak if you have questions to Paul.
And Julie, of course, as well.
Of course, Julie, yes.
Here.
I'll go ahead if I may. Since I'm not sharing this session, like I'll view myself as a guest. Yeah, thanks a lot. So if I understand the epistemic risks, I mean, you're right to point out that there's a lot of uncertainties, unknowns, kind of before you even start developing a machine learning system. To me, in a way, these epistemic risks that you're pointing to, I would understand that as one of the sources of opacity, actually, right? So, I mean, in a way, because you don't know the biases in your data set, or even don't know a lot of the details about your data set, let's say, or don't know a lot of the things about the algorithm, the way it works, especially some machine learning algorithm, that's then going to be the reason why opacity comes about. Is that right? Just trying to clarify here the relationship between concepts.
Yeah, okay. I'm not sure if this is really what we want to would agree with. So also beforehand, I don't know if it was in your introduction or if Katie stated that there are sort of 3 reasons for the opacity, and I don't think any of sort of this risk or decision making in the beginning of the development phase don't really play into this. So because I don't think it's really complexity. So we can't really make the connection from these decisions to complexity directly, at least, I think. And I think the other 2 categories don't really fit. Either you make an argument for the complexity part or not. And so, I mean, if we learn much about the potential sources of epistemic risk, it also won't really help to resolve the epistemic opacity directly, because by learning about all these sources of epistemic risk, we will not know how the neural network comes up with a solution. But the thing that we might learn from it is sort of what are actually the driving forces that what are there proxies that sort of lead to the decisions, or did we sort of make sure that this doesn't happen?
Okay, fair enough, yeah.
So, are there further questions? Julie, do you want to add something?
Maybe, yeah, I could just briefly add to this entanglement between opacity and the epistemic risk perspective. So that mainly, or maybe the main intention was to outline how machine learning systems are something purposeful that relies on decision making, and that therefore, when dealing with all these different challenges that we mentioned in the beginning, such as providing explanations or justifications and so on, we do not only want to know the precise way in which the model comes up with a certain result, but we then, as Sullivan, for instance, has pointed out, we are also interested in knowing that not only why this particular path, for instance, has been taken, but also what are the assumptions that underlie the modeling process. And so we think that the notion of, or the framework of epistemic risk may be fruitful to put together both of these aspects. But yeah, so I would certainly agree that both may very well be entangled.
Cool, yeah. I think this might also connect to some of the things that Vincent Miller is going to talk about later, but maybe we'll see about that.
Yes, and it's a pity that Emily is not here because her ears are ringing, I'm sure. Who's now at Eindhoven, like all good people. So.
Okay, thanks. Then a big thanks to Paul and Julie for their interesting talk. And yes, also to Katie, of course, for her talk. The next one then is Lok Chan, and he will give us a talk on explainable AI and epistemic representation. Lok, do you want to try to share your slides?
Yes. Let me go ahead and do it.
Maybe we should also wait another minute just to give people the chance if they're switching from another symposium. I think we're one.
Yes, of course.
You guys able to see my slides okay? Yeah.
Yes.
Okay, just let me know when you'd like me to start.
The moral AI lab. I like it.
Yeah, the joke is sometimes I call it the more AI lab. We need more AI, more AI.
Well, more AI is not always moral AI. I think.
Exactly. That's what I was thinking. Even though that's what it feels like sometimes. We just want more AI, not moral AI. But that's my own interpretation.
Whose lab is this?
So this is a interdisciplinary lab on the philosophy side, involve Walter Armstrong. In the computer science side, it was with Vincent Conitzer. They're all at Duke. And then Jenna Scheiborg is the data science side. So it's kind of interdisciplinary, and I'm kind of stuck in between and
Cool.
getting all the different perspectives.
Shall we then proceed? I think we're, yeah.
Okay, sure.
I think go for it.
Okay, so hello everyone. Is a good morning for me. Actually, thanks to this conference. I haven't been able to get up this early for a long time. I'm in East Coast, United States. So my name is Lok Chen. I'm a postdoc at Duke University, and today I'll be talking about how explainable AI can be seen as a kind of epistemic representation. It's just to shift the focus from explanation to representation a little bit. And I want to kind of examine the kind of implication and kind of what it means if this is possible. So again, the black box problem. I'm not going to belabor too much of this because I'm sure the previous speakers, and the introductory session that we had this morning, I think has talked about this problem pretty in depth, and so I won't belabor this. But again, the basis of it is just that we have this model where we know what the inputs are and we know what the predictions are, but we don't know what's going on inside. And one reason for that is a structurally complex model like a convolutional neural network that have seen a lot of success, especially in things like image recognition, right? And believe it or not, this is actually a simplified version of a neural model. Another case, and I will talk a little bit more about this since this particular example will come back, is proprietary algorithms where the inner working of the model is deliberately hidden away from people because it is a trade secret. And one example that has become almost a little bit notorious is what is called Compass, right? It is a algorithm that is used, a model that's used to determine the risk of recidivism for inmates. Sometimes they're not even inmates, people who are arrested, right? And so sometimes these models used to determine whether these people should be released on bail, and sometimes it is used to determine jail sentence. It is used is currently being used in a wide range situation in the United States, and there was a huge law that was passed in the Trump era that may just make this even more prevalent. And in this particular case, this model, it has over 100 inputs, include things like priors, convictions, even ask questions about the past family, criminality, and it also includes questions about their moral views and things like that. It is a really long list of inputs they have, and output after you put this information in the black box. And again, this information could either be self-reported or a judge may be able to assess the arrested person's background to put this in. And output is like three kinds of risks, whether the risk of the arrestee will commit violent crime again, things like that, right? So we have the input, we have the output, but we don't know how these risks are generated. So there are different responses, and I think this has been talked about a little bit already, but I just want to be clear about these terms so that we know what we're talking about, because I know that this terminology is not set in stone, especially between different disciplines. And I'm not arguing there has to be one way or another, but I just want to be clear what I'm talking about here, right? So I'll be talking about two kind of responses, and the first one is what is so-called interpretable AI, right? Is that, and Cynthia Rudin, who is a huge proponent, and I'll be talking more about her views throughout this talk. But her general attitude is that while we should stop using these black box models, right? Instead, we use something that's interpretable. Now, her part of her research project is that it's both normative but also descriptive, because she really argues for the view that what she calls interpretable models are just as reliable, as trustworthy as complex black boxes. Now, what does she mean by interpretable model? Well, she means something that is kind of humanly understandable, and that is kind of a general idea. So, and this is her work, her example, right? So, for instance, she has this is a machine learning model that in the sense that it's trained in data algorithmically, right? And the output is a set of rule sets, right? So her idea is, well, if someone is being predicted is to predict arrest within 2 years, right? A model like this, right, is immediately understandable, as in, oh, you know, maybe if you're age between 18 and 20 and you're male, then you know why you're being arrested. So her argument is that, well, we should just stop using, in the title of a paper, stop explaining black box models and use the interpretable model like this one below. So there's one response, right? The other response, again, which is the topic of this conference symposium, is that while we go for something that is called explainable AI, at least that's what I take this terminology to mean, right? Is while we still retain the black boxedness of this complex model, right? However, well, we do know the inputs and we do know the kind of predictions they will make, right? So the explainable AI schema, right, is to use the inputs and the predictions as training sets and to train models that are interpretable, kind of like the ones that you just saw from Cynthia Rudin, right? But this model here, right, the job is to explain the black box model by giving predictions that at least approximate the original model. Now, that is where a lot of dispute comes from, where, well, what does approximation means, right? And what is the relationship between these two models? And that is the main theme of this talk. And computer scientists have taken this schema to pretty seriously, right? I think this is just a few years ago now. They have proposed this model called LIME, local interpretable model, and Knox explanations. And I think there will be a talk later that talks about this specifically. But general idea is that now they take the schema and what do computer scientists do? Well, more AI, right? They want to use an AI to come up with explanation for this. I'm not going to go into the technical details of this. So these are the background. So now, go back to Cynthia Rudin. Regarding the nature of this explanation, what I want to start with is her idea that there's something fundamentally self-defeating with respect to using explanation to open up the black box, so to speak. And just a little, the motivation should be clear, right? If she wants people to use interpretable models, it makes sense that she want to argue against the very idea of using black box model. And I think this is a nice little argument. I will tell you what I think of it later, but I will just read this quote because I think this is a very nice, brilliant argument. So her argument is, well, explanation must be wrong. Explanations, again, are models, proxy models, right? Post hoc models that are used to explain black box model, right? well, why are they wrong? What wrong? Well, they cannot have perfect fidelity with respect to the original model, so they must be different, right? Okay, but if the proxy model was completely faithful to what the original model computes, right, then the explanation would be the same as, will be equal to the original model. Then we don't need the original model in the first place, right? Only the explanation, right? Well, let's unpack this a little bit, right? So her argument is basically saying, well, okay, you have this black box model, right? Now, if we train this interpretable proxy model, right, in such a way that it always makes the same prediction as the black box model, then why are we even using the black box to begin with? That's her argument, right? And in that case, she still wins out, because that means that an interpretable model is just as good as explainable AI, right? So it is kind of nice. There's a nice logic to this as what philosophers would call argument by cases, right? Or mathematicians would call argument by cases, right? Either the explanation are exactly the same as its target model, then we don't need the target model. Or if it's not the same, well, then that means they're wrong, right? So there's a nice logic to it, right? So that's our argument, and I use that as a starting point for what I want to talk about. Of course, for the interest of time, I will just put my cards on the table, as in what I think of it, right? So what I think of it is this: Rudin's argument showed that if fidelity, right, understood as something like similarity, right, or resemblance, right, in some sense, right, if fidelity is the only measure of success for this proxy model, then I agree with her that using the fair idea of using proxy models is self-defeating, right? So I accept that particular inference, but I do not accept the premise, as in I argue that fidelity, resemblance, and similarity, they are not the only measures, right? Well, what does that mean? Well, to make this argument, right, that's when I introduced the idea of proxy models as representations of the targets. So that's where I suggest a shift from thinking of this explanation as explanation, but at the very least, in addition to thinking of them as explanation, we should kind of think of them as representations. And you can see that coming out even from computer scientists like Rudin and people who are proponents of explainable AI. They talk about proxy models as representations. Even though very soon, because of one reason or another, very soon they will move to talking about them as explanations. Now, let me just be clear, they can be both things, right? But I think to start thinking about them explicitly as representations, right? Opening up us to think of them not just in terms of how similar or how faithful they are to these target models. And that will kind of open up as well to think about what they are and what makes them good representation or what makes them a misrepresentation, right? So that is kind of the background, the kind of line that I want to push. And now kind of shifting gear to philosophers, right? Because philosophers, they care about this idea of representation for a long time, either in the context of art, right? Socrates. Now we're going from AI to Socrates, but Socrates, there's a dialogue called Craterus, right, where he talks about what a good representation is. And one of the arguments that came out of it is that, well, a good representation is not a replica, right? Because a replica is a replica, whereas a good representation is not just to reproduce its target, because his argument goes, well, if we just reproduce it, then it is just you're just copying it. You're not trying to represent it. Now, obviously, because of time, I'm not going to give a careful account of representation. So I'm going to give a quick and dirty version. So it draws inspiration from Gambrai who's the art philosopher of art and writers of art, Nelson Gilman, Paul Taylor, Ren Frosten. So these are the people who care a lot about representation in different contexts. But they both things, right? They all things that, well, one of what representation can do is allow you to learn something about this target, right? So I'm just going to summarize this kind of rough account in four points, basically, right? So representation has a perspectivism that's latent to it, right? The idea is that representation presupposes some kind of perspective of the representer, right? It's hard to evaluate a representation, or whether it's a good representation, without taking account for the values and goals and the intention of the person who's doing the representing, right? And there's also an aspect of pragmatism to it, right? As in the success, right, of representation is determined by how it serves the aims of its user. And also there's the idea of virtuous distortion. Is the idea that, well, sometimes to represent, right, you want to distort aspect of a target in order to highlight a particular feature that you are interested in, right? A feature that you consider as salient, while in the context of your values, goals, and intentions, right? Very lastly, there's the idea of surrogative reasoning, as in representations, right, must allow users to draw some inference, but a good one will be reliable inferences about its target. Now, so this is a rough and quick and dirty account of representation that I will suggest as being useful and helpful to understanding explainable AI. Now, in a quick example, an example that philosophers they did like a aspect of Rudolf Carnap in the 30s. They like to talk about is the subway map. So this sucks because initially we're going to talk about this in London, and I'm going to use the map of the London subway map to talk about this. But such is life, right? But one example is the subway map, right? So the idea is the subway map, right, as a map of the topological area where the subway located in is a poor map in the sense that the scale and the distance are highly unreliable. They do not correspond to the actual topological topography of the area, like at all, right? But it is still a good representation of the subway because the goal, right, is to represent the structure and the network of subway, the system, right? So they like this example because this is a good idea, at least a nice illustration of virtuous distortion, because it's distorting the topological area in order to illustrate certain structure. As a matter of fact, if you look at the original map, right, they try to accurately represent the geographical areas, and it was like a horrible map. People hated it, and when they come up with something that's very clean, then it becomes then this idea of subway map really took off. Now, okay, so there was a quick rundown of epistemic representation. Well, so how does that apply to AI and the use of AI, right? So, like one example that I think the idea of epistemic representation is very useful is understanding that the criticism that people have made against Compass, what I talked about at the beginning, right? So this is an article now, it's like 5 years ago in ProRepublica, right, where they actually build a proxy model to explain to represent the Compass, which is black box, right? And they make the argument that it is biased against blacks, right? So a quick overview of what they did was that they went to a county in the United States where they can request the inmates demographic info such as age, gender, and race, and the prediction that's made by Compass. Now they don't even have the initial input of the model, because those are federal they're federal documents, right? There's a limitation as to what they can request, right? So this departs even further from the kind of expandable models that we were talking about, right? The thing that they have is the output, right? And the certain information about the people's information who was put through this black box, right? So long story short, right? They use a logistic regression, which is arguably interpretable. It's definitely a first much simpler models than something that is black box. And they argue that well, when you run the analysis based on the risk score and the information of the inmates, right? Then you see that, well, being a person being black, right, is statistically significant, right? Because it implies higher probability of recidivism according to this model. Now, I argue is a kind of representation that we can see as a epistemic representation. Now, clearly, if we accept that the black box as a black box, right, there's no way we could go in the black box, and that's just a given, right? Now, but these are, I suggest, a representation that allows us to see the general behavior of the model, and once we kind of let go of the idea of similarity, we can use these models as signs, as a way so we can kind of take a peek into what the general behavior of the black box is. Now, this is not to say we should just accept any kind of black box, take any kind of representation as being true, right? As a matter of fact, if you look at the analysis of Republica, there are some questionable things that they did in modeling, but that's the idea, is that, well, we can look at this model, these interpretable models, and criticize them, and at the end come up with a better explanation at the end. So this led to the idea of a proxy war, right? Well, representation or explanation should not just be seen as like one shot kind of thing. And this is exactly what happened, right? This article caused many other researchers to do more representation of Compass, right? And
Doc,
yes,
may I ask you how many slides are left?
Oh,
because
this is the last.
There are only two minutes left before we go.
Yeah, so this is the last one.
Okay, thank you.
Yeah. So the idea is that is through this proxy wall that we can see whether or not a black box can be accepted, right? So main takeaway, right, is the three things. If fidelity is treated as the only measure of success, the explanation AI is self-defeating is Rudin's argument, right? As epistemic representations, proxy models can be.
Oh, did he just disappear?
Yes, he disappeared. It wasn't me.
I was going to say that's a harsh way to
Kick him.
Let's give him a chance to come back, I would say.
Yes.
Let this be a warning to all future speakers. If Hannes is chairing, he'll just cut you off. No.
Yeah, it's the second one who fell into the black box.
Just have to hope he realizes that he got out.
He's just rejoined the main session. We'll have to join our breakout room.
I think that was his last slide anyway.
I've added him.
Hi, Locke.
I'm sorry, I froze at the last minute. I'm sorry about that. But it was the last slide. I was just wrap. I think you guys just missed the wrapping up. So that's the idea. So thank you. Just want to say thank you.
Okay, thank you, Locke. Yes, and thank you for elaborating on Rudin's self-defeating argument and for sharing your thoughts on her argument and your idea of epistemic representation. So one short question before we go on to the break. Yes, Marinos?
Hi, I was just wondering, so one of the reasons we can have epistemic representations which are not, which leave some of the picture out, and that's fine, is because for any particular investigation, we're not trying to do everything all at once. We're not trying to explain everything all at once. That's one of the reasons we can do it. But isn't it a problem that the kinds of domains where machine learning models are the most useful is where we're trying to do comprehensive judgments, right? Like, simple example, in a hospital setting, there's successful machine learning models for predicting sepsis in patients. They work by taking like the full records of the patients, checking more details and in finer detail than humans are able to manage. And these machine learning models are successful because they are judging everything all at once at the same time. Isn't there a tension between this epistemic representation where we're throwing away some features and that's fine, just like the subway map throws away topographical distance, and the kinds of things where machine learning is the most useful, where we are trying to manage everything all at once?
Okay, the answer has to be shorter.
Yeah, sorry. So a short answer would be, it depends on what you mean by everything, right? If everything by all the features that are used to determine one particular data point, then I think it has to be everything. But there's another sense of everything where we are looking at all of the predictions that a model can make. Then I don't think that is required of the model. Just a short, but there's an excellent question.
Okay, then I would say thank you, Locke, for this for your great talk, and we will now go into the break. And after the break, we will hear David Watson on no explanation without inference, and we will see here in 8 minutes.
Thank you.
Thank you.
Okay. All right, so next up we have David Watson, not of Oxford, but of UCL. We'll be talking about no explanation without inference. Go for it.
Yeah, so thanks, Carlos and Hannes, for putting this together. I know it's been kind of a long time coming. And thanks to all the other presenters who have done really great work earlier today, and I'm sure we'll continue to later in the day as well across these various time zones. So I'm going to present on something perhaps a bit narrower in scope than some of the stuff we've been seeing so far, but I'm happy to branch that discussion out a little bit, maybe in the Q&A comments after. And the title, as Carlos mentioned, is No Explanation Without Inference. I'm going to talk a bit about severe testing and interpretable machine learning. So kind of just a quick overview of what that is going to look like. I'm going to say a few words about interpretable machine learning. I think this crowd probably knows a bit about what I mean by that, also known as explainable AI, or in general kind of issues surrounding opacity in machine learning. I'm going to say a few words about severe testing after that, and I'm framing that very much in the work of Deborah Mayo and sort of the error statistical philosophy associated with her in that work. And then I'm going to talk a bit about the kind of intersection of that Venn diagram, if you like, on how these two don't really fit together right now, but maybe should. Right, so without further ado, I'll just jump right in with the interpretable machine learning bit. This is a basically random list of things machine learning is used for in your daily life that you might encounter. Just kind of trying to drive home the point that this technology is everywhere. It is in very important sort of public and private applications, but it's also just kind of used in more general low stakes ways. I take it that these instances are fairly unobjectionable, at least for the most part. But the thing is that that's not all machine learning is used for. It's actually also used in some other more high stakes, potentially more objectionable kind of applications. And this is another basically random list of things that might occasionally anyway have people sort of scratching their heads asking if this is really something we want to be automating at all. And to the extent that we do want to automate it, maybe it's important that we have some sort of auditing mechanism to ensure that these predictions are reliable, that we understand why those predictions are coming out the way they are. Typically, we associate this with like high stakes settings. So healthcare applications, criminal justice, as was discussed just in the last talk, and other sort of applications like that. These are cases where explainability becomes quite important. Now, there's a ton of different options out there in the interpretable machine learning landscape. There's intrinsic methods, there's post hoc methods, there are global, there's local. For the sake of concreteness, I'm going to stick with the feature attribution framework. And I think this has already come up a few times in previous talks. So like Lime and Chap would be kind of the canonical examples of this. But really briefly, the idea with these sort of local linear approximators is that you've got some wiggly function, that'll be the curve in blue here. And the thing about any continuous function is that if you zoom in to any point on it close enough, you can get a linear tangent. And this is the basic premise behind Lime, Chap, and things like that. So if we're interested in this point A, we want to explain why the model predicted whatever it did at that point. We don't really have a notch on the y-axis, but it predicted something. We're going to zoom in, and we're going to get this green line, and we're going to say, well, what's the formula for that? And the idea is that linear formulas are somehow more interpretable because they give us like nice weights. So in this case, a very simple case where there's only one predictor, there's a positive weight on x. We say that an increase in x is associated with an increase in y, at least at that point. So this is arguably helpful, potentially could be problematic in really high dimensions or something, but this is the sort of model I'm going to be thinking about. A lot of what I'm going to say, arguably everything of what I'm going to say, actually applies just as well to other popular interpretation methods, so like rule lists or counterfactuals, which you can also talk about maybe a bit in the comments or something if you like, but I'm just going to stick with this for concreteness. Okay, so much for interpretable machine learning. So let's talk a little bit about severe testing and what that kind of means in this context. I mentioned earlier that I'm thinking really of the work of Deborah Mayo here. So if you're unfamiliar, Deborah Mayo, over the course of the last, let's say 20 or so years, has been putting out a series of sort of articles and monographs that develop this error statistical philosophy. She's working kind of in the philosophy of science, philosophy of statistics framework. And if you could kind of boil this down to a claim, it's the severity hypothesis. It's kind of posited in several works of hers. And that's that data X provide good evidence for hypothesis H, just to the extent that H has passed severe test T with X. That's a lot of letters, and I'll sort of unpack that in a second. But if I could sort of ground it for people, if you're unfamiliar, sort of ground this in things that may be more familiar, I think she's very much working in the tradition of Popper and trying to maybe take one step beyond Popper's kind of negative conclusion, which is that science advances knowledge by falsifying hypotheses and saying, well, no, we can actually have positive conclusions to the extent that severe tests are passed. And that's sort of a defeasible way to salvage something like induction. She's very careful to not sort of overcommit there, but to say that we can, if we refocus from the hypothesis itself and placing like a probability on the hypothesis and saying, no, it's more about the testing procedure. If the testing procedure is rigorous, and I'll unpack what I mean by a rigorous testing procedure in a second, then we can gain sort of warrant for believing in certain hypotheses. Those can be justified to various degrees. Okay, so what's a severe test? And how do we sort of locate all these variables together, our H's and T's and X's? Well, there's two criteria really for a severe test according to Mayo. And the first is that we're gonna have this testing procedure. It's gonna take some data X as an input and spit out, let's say 1 or 0. You either did or didn't pass the test. And for a given hypothesis, we say that that hypothesis has passed the test with data X if, first of all, the outcome accords with the hypothesis. That's pretty common sense. And then the second criterion is that with high probability, that test would have produced a result that accords less well with H if H were false. So taken together, these two, which again, pretty common sense, I think. It'd be hard to really object to these. Taken together, these sort of amount to saying we want tests that are sensitive and specific, that tend to have low false positive rates and low false negative rates. And ideally, in a sort of perfect world, we would have testing procedures that assure us to get all and only true outcomes. That's a high bar, an unrealistically high bar, but that's sort of the ideal that we're striving for with these severe testing procedures. So what this means in practice, and this is where Mayo, I think, goes a bit beyond Popper, who I think would have agreed in principle with everything there, but he doesn't really unpack the implications of this. And for Mayo, this is all boils down to statistical inference. That is the actual way we go about severely testing things in the real world. So Mayo is very committed to a sort of frequentist interpretation. She really develops this in the theory of like Neiman-Pearson testing, uniformly most powerful tests, that kind of thing. This very explicitly is committed to Mayo's vision of severe testing in the sense that the whole sort of framework starts with some fixed false positive rate alpha, or some level of the test, and then tries to minimize a false negative rate beta. But I don't want to dwell too much on that because it's important to acknowledge that everything Mayo says applies just as well to a Bayesian framework, and Bayesians and frequentists are going to disagree on a million things to do with interpreting probabilities. All those debates are kind of beside the point, because even in Bayesian inference, we're going to have some decision criteria. Maybe it's Bayes factors, maybe it's credible intervals, and there have been Bayesian sort of interpretations of Mayo's work that show the close similarities between these two. I also don't want to pretend that those are like the only ways you can think about these problems. In machine learning, there's a lot of emphasis on cross-validation and sort of predictive checks of different kinds that are not necessarily committed to Bayesian or frequentist interpretations, or maybe even some hybrid. And those would also broadly fall under the same testing framework. It's just about these two criteria, sensitivity and specificity, however you're going to cash those out. This should all feel pretty familiar in the sense that if you've ever even taken a fleeting glance at published results in the natural or social sciences, you might have noticed that the way it works is you do a test and you report the results. So maybe that means a p-value if you're a frequentist, or some kind of effect size with a confidence interval, or a Bayes factor, or you have to talk about the power of the test. That's how you're going to talk about sensitivity. These are like the elements of science, right? This is how you go about sharing your results with the world. And if you didn't have these sorts of things, it would be very hard to get published, generally speaking, in the natural or social sciences. We don't hold interpretable machine learning to the same standard, at least not typically, and definitely not with things like Lyman Chap. We don't do this sort of severe testing with these, and it's unclear why, because at the end of the day, you're making empirical claims with these methods, and empirical claims can, in principle, be tested. So this kind of brings us to the intersection point. What does severity and interpretable machine learning have to do with each other? Well, I'm going to highlight two issues in particular that seem especially salient. There may be others we can talk about as well. The first is scope ambiguity. So here's a figure actually from a paper by Wachter et al. This was introducing kind of counterfactuals, which is another big approach in interpretable machine learning. And what this figure is trying to show you is that if our target function is that wiggly thing, and our prediction we want to explain is the little x on that wiggly function, you can actually get a whole bunch of different lines that are going to assign different weights to that x variable, a positive weight, a negative weight, a zero weight potentially, depending on the width of your linear window. So that actually turns out to be quite important. And in practice, that window amounts actually to a sampling procedure or a weighting procedure, giving some density around x. And Chap and Lime have their own approaches for how to do that, but they're quite heuristic in the case of Lime. There's a bit more theory behind it in the case of Chap, but you can still get a lot of instability around very nonlinear regions of a regression surface or decision boundary. So the point here is that these feature attribution methods, they're not really providing any information about the scope or fit of a local linear approximation. They're just going to spit out a scalar. They're just going to say, this is the weight on, say, x. But if you were to resample that, you might get a very different result the second time or third time if it's a wiggly part of the feature space and that local linear window is not being well reported. So this is not being severely tested in this case. There's no sort of goodness of fit measure. There's no concept of quantifying the uncertainty around this. A second issue that's very important here is confounding. And confounding is arguably not the term, because that sort of suggests a causal interpretation, which may be applicable, but it's actually even a simpler problem. It could just really be associations in the first place. And I'm thinking about this primarily in the context of like algorithmic bias here. So we've had a few speakers sort of talk about the close affinities between issues in algorithmic bias and explainability, fairness and explainability. And the issue is that when you've got highly associated variables, say you've got maybe some permissible variable that serves as a proxy for a sensitive variable, this has been shown with maybe zip code predicting race, for instance, you can exploit that to make a potentially biased algorithm appear to pass some sort of algorithmic audit or appear fair in user studies. Now, in general, these feature attribution methods are going to struggle with collinearity for the same reasons that a regular linear model struggles with collinearity, and you've got to sort of deal with that usually with some either regularization method or something else. Those problems could be that it's either splitting attribution evenly across the two in a way that could be unfaithful to the target function, or depending on the regularization you're using, it could just randomly select one of those two highly associated variables and exclude the other because you can reconstruct it. This is a problem. This gets back to the sort of fidelity issue. And it just takes a little bit of association between variables to introduce this. And without some sort of testing procedure or extra information beyond just a scalar weight being assigned to a variable, it's very hard to identify and sort of mitigate against this problem. So I'll just sort of wrap up here with some of the takeaways of these sort of problems, and that is that these misleading attributions, they can be avoided by severe testing. And we've got methods of doing this. You're just going to need to quantify the uncertainty associated with those coefficients and give some goodness of fit measure for the linear approximation itself. These are well understood ideas in linear regression. Unfortunately, they're a little bit difficult to apply directly with Lyman-Schaap because of the weighting and sampling procedures associated with them. So typically, if you were to really rigorously get like a full confidence interval, say a prediction interval for these coefficients and some sort of goodness of fit measure, depends what kind of model we're talking about to see what would make the most sense, you're going to have to do some kind of complicated resampling procedure. But you know, I think that's important in interpretable machine learning because there's often this talk about trust in this area. We're always talking about, can we trust this model? Why should we trust this prediction? But it's unclear that we should really be trusting the outputs of methods like Lyman-Schaap. I mean, at least the target function presumably has some error measure on a test set that made us go with it in the first place. Whereas Lyman-Schaap, there is no way to rank the reliability of its individual explanations. It is not clear from the default settings of Lyman-Schaap whether we should put equal faith in every single prediction that they make, or if some are better than others. There needs to be some way to quantify that and rank that. Feasibility is a legitimate concern here. So the resampling procedures I'm talking about for doing this in a rigorous way, like for instance, bootstrapping, will slow down a method. I mean, I think some of the popularity of Lyman-Schaap comes from the fact that they're quite fast and really easy to work with. But when stakes are high, so when we're in these sort of situations like I had on the right column, that earlier slide, if we're talking about healthcare, we're talking about criminal justice, then the explanation kind of needs to be right. You know, it's not good enough to just get it quickly. So to the extent that we care about that explanation being reliable, trustworthy, we're going to need to introduce some sort of severe testing framework to quantify that uncertainty, bound error rates, and be sure that we really know what we're talking about here. So I'll just sort of conclude there, and I'll stop sharing. And I'm happy to take any questions or comments that people might have at this time.
Thank you, David. Yeah, that was really nice and clear and interesting. Does anybody have any questions? Again, as usual, just feel free to talk or put it in the chat if you prefer. Or wave your hand and I'll call on you.
It looks like maybe Locke's got a hand up.
Oh, I don't see him. Okay, sure. Go for it, Locke.
Yeah, so at one point you asked you raised the question of why computer science, why machine learning models are not subject to questions regarding severity or things like robustness of their inference. I almost wonder if there's like, well, I almost wonder if there's no discipline answer to it, but more of a sociological. Like it's like computer scientists, they're raised by just looking at the data set and just looking at accuracy within the set of the data instead of worrying about how it relates to the world. Like that's kind of how you kind of think about it. Like, what do you think about that kind of answer to that question?
Yeah, so that just reminded me of a paper. People may be familiar with this. I'll just put it in the chat. You maybe know this paper, The Two Cultures of Statistical Modelings, from Leo Breiman in 2001. I think it totally sums up what you just described in this really nice way, and sort of talks about the difference between statisticians, sort of a classical, you know, like parametric inferential sort of framework, and at the time a very nascent, he's writing in 2001, sort of culture, if you like, or philosophy of what ends up becoming like machine learning, sort of a more computer science, like practical applied approach. And I totally get that. I think there may be different starting premises, different systems, and yeah, cultural sort of philosophical differences that go some way toward explaining this. But I think there's a growing awareness in the statistical literature anyway that that can lead us astray in a lot of cases. So like for the things that got us to where we are in the sciences, to this point where we kind of need to be rigorously testing and we need to be bounding error rates and quantifying uncertainty, that took a long time to get us there. And we can kind of import those lessons quite directly, I think, in other areas, and it's fruitful to do so. It's potentially time consuming, it's potentially annoying, but you can save yourself a lot of headaches, I think, by bringing that kind of rigor into these settings. And when stakes are high is when it's really important. So I'm not saying that this is like the only way that anyone should ever use algorithms. Like, no, if you're, you know, optimizing ad revenue, God forbid, on your website, maybe you don't care about p-values. Like, that's probably not a top priority for you. But when you're making healthcare decisions, when like we're deciding about, you know, potentially invasive treatments for someone, or like criminal justice applications, then I think we need to bring the full weight of you know, scientific knowledge and inference to these sorts of decisions. I mean, these are high stakes decisions that where a lot might hang in the balance.
Yeah, cool. Thanks for this elaborate answer. Based on all the cameras turning on, I suppose that means that there are questions that want to be asked. I saw Katie's camera turn on, or does anybody want to ask a question? Konstantin?
Yeah, thanks. I really appreciate the change in perspective. But so I guess explainable AI is sometimes framed as this like client satisfaction kind of problem, and you're pushing us back to like, well, if what we're talking about is why we should trust machine learning systems, it's kind of the reason we should trust any scientific theory, any mechanism in social science, and it is subject to the same norms as any scientific theory. And so what we have to talk about is then like scientific methodology and the kinds of reliability guarantees that we can expect from our best scientific methods, or something like that. So to really solve explainable AI, what we need to do is like philosophy and about methodology of science, or methodology of science, and what reliability means, how reliability depends on how difficult the problem you're trying to solve is, and what the best you can do in this situation is from a complexity type perspective. But does that just mean like explain there? Is there some space between these two views where like we're not explaining ourselves to society, but to, I mean, it makes sense that, you know, if we're building a compass, we have to explain ourselves to society. And if we're building, you know, something less low stakes, but you also want to explain yourself to the individual. So is there some space between those two things, or is explaining yourself to the individual really just bringing in the whole, all the questions of scientific methodology and, you know, philosophy of science from the beginning of time?
Yeah, I'm inclined to the latter personally. I see no reason not to bring in that machinery, since it's pretty successful, all things considered. And you know, if it again with the caveat though of like when it matters. So I don't want to create some sort of like impossible regulatory regime where firms are afraid to use this technology because using it requires this like complicated publication process and peer review, and like that's, you know, not something they can do on their time scale or something. In a lot of cases it probably doesn't matter, and that's fine, but there are cases where it matters, and I think Compass is like a pretty obvious example. I tend to think a lot more of like medical stuff because I've done work in bioinformatics, and there's lots of like diagnosis algorithms that are out there, things that are being used to recommend treatment regimes and stuff. And those are cases where there's, first of all, already like a pre-existing culture of testing things really rigorously and kind of going with like evidence-based conclusions or whatever. But that reasoning seems to go out the window as soon as an algorithm comes in. And that's what I find so like mystifying, kind of like why that happens. Like, it's not impossible to test these things. We know how to do it. We know the methodologies that work, but we just don't seem to.
So the justification in medicine is you have to point to an RCT that's showing the algorithm is good or whatever. Is that the idea?
RCT is a high bar in a lot of epidemiological settings. It's fine to just have some causal assumptions that we start from. I mean, causality is going a bit of a different direction. Depends what we're talking about, right? Like if we're just talking about tumor diagnosis, where I'm showing you a picture of a tumor and you're telling me if it's benign or not, I don't know that we really need to bring structural causal models into that. That's just like a classification problem. But yeah, I mean, to the extent that causal things matter, which they well may, if we're talking about like biomolecular settings, then sure, we want to bring in the kind of that artillery. But this thing of kind of letting Lime and Shap just speak and taking those scalars at face value, I think is just obviously problematic. And we need some way to just quantify that uncertainty. And we know how to do that because we've done it for 100 years.
Cool. Yeah. So that kind of, oh, sorry, does somebody still have a hand up?
I think Katie.
Oh, Katie. Okay, well then maybe we can do a quick question, since technically we should be moving on, but go for it. Go, Katie.
Sorry, I will talk super fast. So thanks for the talk. I just wanted to ask, so I think the scale that you sketch from, you know, ads doesn't really matter, biomedical or scientific cases does matter, it's plausible, but it strikes me that figuring out what the gray area is and where lines should be drawn in the gray area is actually quite tricky, especially if we're thinking about, let's say like a private company that is developing some sort of automated decision-making system that does have some significant impact on people's life outcomes, but not in a space that's sort of governmentally controlled in the sense of criminal justice or even lending, but might nevertheless, you know, affect the distribution of outcomes or opportunities or chances or whatever. So I guess, like, what would you say there? And to add in one more wrinkle, I'm curious about what you would say about data that might contain some sort of artifact, some sort of like significant influence of the way the data was collected, or arbitrariness in the data that you know is a very strong correlation, but in science we might want to work very hard to get rid of that. But in these more social regimes, is there, would you say a similar thing, like we have to eliminate that kind of artifact or correlation?
Okay, I'll try to
quick
answer this quickly. Yeah. So to the second point, I would say Konstantin's mention of like causal inference, either through the form of RCTs or Pearl and colleagues have set up whole ways to try and reason about causality without RCTs, would need to be brought in if there is good reason to believe that there are spurious signals and associations. Yes, yes, we need to try and ameliorate that for sure. I'm not saying that's easy, but that's, you know, a priority for scientists to try and do that. The other question I think is harder, the one about like, you know, where do we draw lines? There's no simple answer there, right? Like that's a policy question, potentially an ethics question, and I expect those things to be contested. But that's fine to say it needs to be contested, and we can, you know, talk about a case by case basis. I think the first step is to sort of acknowledge that a line needs to get drawn somewhere, and it seems to me right now we're not even trying. Like we're just sort of like waving our hands and saying, oh, computers are doing it, so like it's fine. But to the extent that we acknowledge that there needs to be some sort of division, well, then we can sort of have that debate of like, well, what about this case? What about that case? And now we're in like sort of regulatory regimes, and these can be contested and debated in a sort of more public forum. I don't have a general answer to that, but I think that's a conversation that needs to happen.
All right. Thank you, David. Thanks to all the question askers. I would say let's move directly on to the next talk. We have Richard. Is it you presenting, or is it still Harry? I think
it's me. Yep.
All right. So then I would say go ahead and share your screen. We have Richard Tomset, formerly of IBM. Where are you now?
Oh, sorry. I'm going to have to probably sign back into this because of my computer's
go for it.
Ridiculous privacy settings. Not ridiculous, very good, but you know. Okay.
If instead of a talk you just want to give us a guitar solo, I'm sure.
You don't want to hear that. Okay, I'm going to have to quit and re-sign in, but I'll be back in just a second.
Okay. In the meantime, David, we have another comment in the chat, probably interesting for you.
Yeah, I saw it. I would totally agree that Popper is a little harsh on the induction side. And no one agrees with Popper. I don't even know that Popper agreed with Popper by the end. But Mayo, I think, engages with him in a really interesting way. So those, especially like those early things, like her writings in the 90s or whatever, I think is a really nice kind of critical development of that that idea.
All right, Richard is back. There we go. We got some screens. Okay, we see your slides, but not full screen.
Okay, fingers crossed.
Good.
We should be there.
Yeah,
now.
it works.
Sorry about that. Okay. Thanks very much. I think, yeah, so I think this talk has quite a few overlaps with the previous one, but also goes into some slightly different areas. So hopefully they'll complement each other reasonably well. So I'm going to talk a bit about some of the technical barriers to the adoption of the kinds of post hoc explanation methods that came up in the last talk. Quite a few things have changed over the last year since we originally submitted this extended abstract. So Yinjin Lee has left IBM Research. She still works for IBM UK, but she's now trained to be a patent lawyer. Harry and Liam are still PhD students at Cardiff, and I've moved company to somewhere called Onfido. So that's a digital identity verification company. So if you've ever signed up for like a Revolut or Monzo bank account and had to do your ID document and selfie kind of verification process, we do the software that does that. And so there's a lot of very interesting explainability issues and robustness issues that come up in the systems we use there, which we're looking to improve over the next few years. But anyway, I'll get on with the talk. The mouse, there we go. So just to give a little bit of context, and many apologies for the incredibly low resolution graphics that I've been provided here. The work that we've done on explainability, this kind of team of people, is under this program called DIAS-ITA, which stands for the Distributed Analytics and Information Science International Technology Alliance. And so that's headed up by IBM in the US and the UK. It includes various universities in the US and UK, various other industrial partners, but it's funded by the US Army Research Lab and the UK Defence Science and Technology Lab to do fundamental science research on distributed analytics topics. And one of those topics is explainable artificial intelligence, or focusing sort of on the machine learning side of things. So that's kind of the context for this research. I'm going to give you a little bit of a brief background on the post hoc explanation methods. Hopefully those are sort of already a bit familiar to most people here. I'm going to focus specifically on explanations for machine learning model outputs, particularly classification type machine learning models, rather than AI more generally. Then I've got two separate issues that we look at in this paper. The first one is problems with the robustness of the explanation methods, which was highlighted in the previous talk as well, but I can give you some kind of concrete visual examples of some of those issues. And then the second issue I'm going to talk about is this problem with assessing kind of the quality of the explanations that these methods produce. And I'll go into a little bit more detail on one of a paper we published last year at AAAI, which looked at some of these metrics for assessing explanations for image classifiers. So to start with a little bit of background, post hoc explanations, they might well have been identified as a kind of class of explanation well before this, but they kind of gained that terminology, I think, gained traction within the machine learning community, at least after Zach Lipton's 2016 paper called The Mythos of Model Interpretability, which is very famous now. The purpose of a post hoc explanation is to try to explain the output of a black box machine learning model. And usually that's done by presenting an explanation in terms of particular aspects of the input data. And the point of them is that they don't alter the black box model. So you create a machine learning model without worrying about explainability at all. You might not even have direct access to the model internals. And then you have a post hoc explanation method that examines that black box to try and work out why it's provided a particular output given the input. So we have this kind of conceptual model or diagram that kind of tries to put this visually and help think about how we use these terms, and also a definition of how we use explanation versus interpretation. And this is, of course, by no means sort of prescriptive. It's just so that you know how I'm using the terms and what they mean to be, and you can argue about whether that's correct or not, but just for the purposes of this talk, this is how I'm using the terms explanation versus interpretation. So you'd have the AI system, which is your machine learning model. Then your post hoc explanation system would be the explanator that produces explanations. And then the human who is interacting with this system in whatever way would receive that explanation and form an interpretation of how that output from the machine learning model has been arrived at. So interpretation involves humans, whereas the creation of an explanation is done sort of by the machines. And then we have underneath those outcomes, we have the evaluation of those outcomes. So the model you'd evaluate using your standard kind of performance metrics like accuracy or precision recall or any other kind of accuracy kind of measure you're looking at. And then theoretically, we'd like to be able to measure the explainability of the system. So that's sort of the quality of the explanations, and then also the interpretability, and that kind of thing would require human or user studies to assess the interpretability of the whole system. So the first problem we have of these post hoc type methods is problems with robustness. And that's kind of illustrated in this figure from a paper a few years ago. I've misspelled the author's name there, but you should be able to find it if you just type in that title to Google Scholar. It's quite a nice little paper, and it's, I think, quite similar to the point made in the previous talk about the locality of these kinds of explanation methods like SHAP and LIME. So this paper explicitly examines SHAP and LIME as explanation methods. So in the top row of the figure, we can see we have a binary classifier. So the blue is showing regions classified as 0, the red is showing regions classified as class 1. The decision boundary sort of in the middle here I assume you can see my mouse, by the way. And you get, on the left, you've got the explanations provided by SHAP for input data points. The input data is just X and Y coordinates, so the decision boundary is just splitting down the middle. All these points on the left, which are the little blue dots, are provided with explanations in the form of feature importance values. So because the decision boundary is just at 0 on the x-axis, the y-axis has no influence on the importance, has no influence on the classification decision. And so these little bar graphs here are all showing that the x-axis is very negatively important for these decisions and very positively important for these decisions, but that the y-axis value, which would be on the right-hand side of the bar graph, has no influence on the decision. So both for both SHAP and Lime with this linear classifier, they're doing a pretty good job by the looks of things of highlighting the important feature. Then on the bottom row, we've got a case of a non-linear classification problem. And so there's a neural network that's been trained to classify an inner region which relies on both the x and the y-axis and separate out sort of the inner from the outer coordinates. And it's a little bit tricky to see on the figure, but if you kind of scan around and have a look, the green, again, bars are showing you the importance of the x-axis on the decision. The purple bars are showing you the importance of the y-axis on the decision. And you've got some points that are very close to each other, but that have very different feature importance weightings, which intuitively feels wrong. You would expect points that are close together. Some of them that are close together have the feature weightings reasonably similar, but also they don't necessarily seem correct. Like these ones here on the line chart, these two show very negative values for the purple, which is the y-axis. This one shows very positive value for the y-axis, but they've barely changed on the y-axis. They've only moved a little bit on the x-axis, and the explanation is completely changed. So with this nonlinear case, we think that perhaps these explanation methods are not doing so well. So they're kind of lacking robustness in this nonlinear case in that sense. And this results in a few kind of practical implications when using these on more complicated data sets and looking at the explanations they produce. So this is an example. Lime works, part of Lime's workings are that it generates loads of random perturbations of the input data point that you're trying to create an explanation for, and then produces this, for an images, it produces kind of heat map of an explanation showing which are important or negatively important pixels. And because of the randomness, if you reset the random seed every time you run Lime and your model is a little bit, it is quite non-linear and or quite curvy in the area of the input, then each of these runs is for the same input, the same machine learning model, but you get very different explanations every time you run it just because of the randomness in the method. So that's kind of one of the manifestations of this lack of robustness of the method. You also get the possibility to create adversarial manipulations that alter the explanations produced by these methods. So these are different methods. This isn't Lime or SHAP, but there is methods called deep lift and integrated gradients, but they're kind of relatively closely related to at least the SHAP method. In fact, the version of SHAP that works for images is sort of the approximation of it is based on the deep lift method. But again, they're just producing these kind of heat map explanations over pixels. And the idea behind this paper was that they wanted to create adversarial manipulations, so very tiny changes to the input pixel images that are imperceptible to humans, and in fact, not necessarily imperceptible, but unimportant for the machine learning model. So in both these cases, this is a monarch butterfly classified correctly with very high confidence, but they've adversarially manipulated it to completely change the explanation. So this kind of shows another manifestation of this non-robustness that can be exploited or explored by these adversarial methods. And again, another kind of similar approach where they haven't tried to minimally change the image. They've applied what's called an adversarial patch, so this to purpose-made sticker that you put on an image to, traditionally you'd use it to trick the classification. So in this case, it should be classified as a person. Here, they've tricked the system, the machine learning model, to classify this as a sofa. But the GradCam, so this is the GradCam explanation method, it picks out that there's an adversarial patch on there. So that explanation shows that it's not the model isn't looking in the right place, really. And this paper develops new patch methods that both change the classification and ensure that the GradCam method doesn't pick up that there is an adversarial patch in the image explicitly. So there's a sort of slightly exotic side effects of the lack of robustness of the current explanation methods as they are now. Second, we have this problem with assessment. So this is back to the quality of the explanations, and it relates to issues of whether we can trust them, and in what circumstances we'd be able to trust them. So how can we assess the quality of a post hoc explanation? And that leads us to this notion that some authors have proposed that they just call fidelity, which sort of is meant to capture how well an explanation conforms to the actual true decision process of the model that it's trying to explain. And that's easy enough to think about informally, but when you try and define it, as alluded to in the previous talk, it gets tricky. So we want it to be measurable. In this case, it's relating to explainability and not interpretability. So it's about the machine learning models and the explanation methods. It's not about the human interpretation. So it doesn't require human experiments. So we should theoretically, hopefully, be able to come up with some kind of metric or set of metrics to assess this quality of an explanation that we call fidelity. So there was a paper a few years ago that looked at fidelity, not in terms of a metric, but just in terms of a way of assessing whether the explanation methods could in fact be faithful at all, by doing quite a neat little experiment where if we start on the left and move right, what they're doing here is they've taken a neural network with many layers, and they run this image through it, it gets classified correctly, and then the original explanation for that network is in the far left-hand column. And what they do is produce new explanations by progressively randomizing the weights of the network, starting from the output layer and then going backwards up to the very input layer of the model, and seeing how the explanation changes as you affect the model. And you can see that some of the methods, like the guided backpropagation method and the guided GradCam method, the explanation changes very, very little until you go quite far up the model in changing the weights. And even when you completely randomize the weights, there's still a lot of the structure of the input left in the explanation. And the point here is that if you can make random changes to a model, but you still get the same kind or a very similar explanation as the output, that suggests that the explanation isn't really capturing anything fundamental about what the model is doing as how it makes that explanation. So that was an interesting sort of demonstration of the possibility that some of these methods might not really be doing what we want them to do. But how do you capture that in a metric so that you can you don't have to run this individually and run all these experiments with randomizing weights? Well, there's been a couple of proposals. I think I'm sort of pushing my time a little bit, so I'm not going to go into too much of the detail of how they work, but it's for these metrics that I'm talking about here specifically for image saliency map type post hoc explanations, although you could adapt them to any kind of feature importance post hoc explanation. But the idea behind them is that you somehow perturb the input one feature at a time or features at a time, and you measure the change in the model's output classification confidence, and then you do some kind of correlation between how much the output confidence changes versus what the importance assigned to the feature that you manipulated was in the first place. And if the output changes a lot for high importance features, then that's good. If the output changes very little when you manipulate a high importance feature, that's suggesting that the feature has been assigned high importance incorrectly, so that the explanation is not doing very well. There's a couple of different sort of ways of measuring this that have try and kind of capture the same concept but do it slightly differently. So this is just a visual example of how this might work. So this is manipulating pixels by setting them to the data set mean. So it's difficult to see here, but once you get down to about 50 or 60 or 70 perturbation steps, you can start seeing that you're setting all these pixels that are considered important to gray. And other authors use setting it to random RGB values, or it's basically trying to destroy information in the pixels in some way. And when you perturb pixels like this, and then do this for, say, we did this for every image in the CFAR 10 test set, so that's 10,000 images, and then you measure the fidelity scores according to one of these metrics. For different explanation methods, you get these distributions of fidelity scores, which are extremely broad. And in fact, they also rank the methods differently depending on the specifics of how you perturb the pixels. And there's no obvious way of knowing what's the correct way of perturbing pixels, because ultimately you're changing the information in the data anyway. So there's no real sort of set way of doing this. So you not only get very high variance when you use these methods to try and assess the explanations, but you also change the rankings of the methods depending on your implementation details. And this is just a chart showing the same thing for a different metric, and the extremely high variance of that different metric. As you delete more and more pixels, the metrics go all over the place. So we published these results in AAAI last year. The key takeaways were that these saliency metrics, as we called them, for measuring the fidelity of post hoc explanations for image classifiers, they have very high variance, they're sensitive to implementation details, and then we also performed some tests of statistical reliability. So this sort of goes perhaps alongside the severe testing frameworks suggested previously. I don't know if we would class them as severe tests, but there's certainly some kind of statistical test to understand the metrics that we were looking at using for measuring explanation quality. So they were statistically unreliable in three different ways, basically. There's different metric implementations seem not to measure the same underlying concept of fidelity. So the scores that they produced for the images weren't necessarily correlated between the different metrics. The metric scores and therefore the explanation rankings are inconsistent between different images in the data set, and a single metric produces inconsistent results when it's rating different explanation methods over all the images in the data set. So that kind of renders these metrics for assessing whether a particular explanation or a particular explanation method is better than another kind of useless for this particular case. So that kind of brings us on to a discussion point of whether we should be using them at all. I'm sure many of you will be familiar with Cynthia Rudin's work on interpretable machine learning. She argues that no, you shouldn't really use them in high stakes decision scenarios, at least, and makes quite a lot of points against their use, and argues that you should instead try and use directly interpretable models as much as possible, especially because in many cases, directly interpretable models can perform equally as well as black box models, especially if you consider the entire system of machine learning model with human decision maker, and not just the performance of the model in isolation. And additionally, aside from these technical barriers, there are some conceptual and user experience questions to address about them. So even if we can find a post hoc explanation method that is technically sound, and we can in some way demonstrate that using a robust metric, when are they useful? To whom are they useful? For what purpose are they actually useful? Are other kinds of methods or directly interpretable models actually better conceptually and for users as well? So that would require further design and user experience research, and it's important, I think, to do that in ecologically valid context. So there's a lot of research, it seems at the moment, that's done on out of context, say on Amazon, Mechanical Turk, and people just ask people, do you prefer this explanation or this explanation? And that's maybe insight, can provide some insights, but it's never going to give you that much of an insight into how users really experience these in real world use cases. I don't think, anyway. So I think that's me out of time, probably, isn't it, Carlos?
Yeah, it would be good. Just wrap up, right?
Yeah, sure. So that's basically it. There's significant technical issues with post hoc explanation methods as they currently are. I think there should be more research into identifying and addressing these. There's a lot of work being done on methods development, not so much work on refinement and rigorous testing of them. And that's it. Thank you very much.
Cool. Thank you, Richard. Maybe you can stop sharing the slides. Any questions? That was really nice. A lot of very recent stuff. I don't see any questions. I'll ask a question that I guess related to your conclusion, right? So in particular, the robustness issue concerns me, right? If we keep getting a different explanation every time we run Lime or SHAP, something like that. I mean, what would you recommend, right? I know you kind of mentioned, okay, maybe using interpretable methods instead, but do you foresee that there's a way to fix the post hoc methods in the relevant ways to like improve robustness?
I think a lot more needs to be done on understanding exactly sort of what the meaning is of the output of a particular post hoc method in relation to both the model and the space that the data lives in. So especially with the non-robustness issue affects non-linear models more than linear models. So if you are using a non-linear model, which often is the case because you have to, because the data is so complicated, then it's going to be very tricky to understand exactly what a feature importance really means. I think it's very difficult to understand what feature importance means, especially when, like, say, in images where all the local features are more strongly correlated. Correlations between features occur all over the place. It's not entirely sure, clear what those correlations represent until you look at the image as a whole. And does it even actually make sense for something like images to assign feature importances on individual pixel or groups of pixel levels? So I think there's a conceptual issue that needs addressing there, and it also relates to the structure of the data and whether how that looks in sort of data space and in feature space. So I don't have a satisfactory answer other than me rambling for a while, I'm afraid.
It's hard to predict the future, right? About how to improve those methods. Fair enough.
It might be possible, to do a kind of combined. We're interested in doing this of simultaneously making a machine learning model more explainable by a post hoc method. So you kind of have a symbiosis between the post hoc methods and making the model structure and design more amenable to explanation by those methods.
Right. Yeah.
So.
Time for one more quick question. Sorry, we started slightly late this talk, so it's eating up our break, but maybe one more question. If not, then that's fine. Then I guess everybody really needs their short bathroom break. Many thanks, Richard. 3-minute break, or let's make it 4. Let's start at one past the full hour.
Your break was as great as mine. Yeah, let's directly come to our next speaker, Andres Paez. He will give a talk on humans that engage in robot mind reading and on the question whether the development of mind readable robots is compatible with the goal of enhancing transparency and understanding in automatic decision making. So I would just say, Andres, can you try to share your slides?
Yep.
Okay, great. Then,
okay, great.
If there are no further questions, I would say just go for it.
Okay, thank you. First of all, I should thank Carlos and Hannes for organizing this symposium. It's been a lot of fun. My background is in epistemology and the philosophy of science, and this is my first AI conference, so I'm really excited to be here. I'm going to be talking about robot mind reading, and I guess the first question is, well, what exactly is that? So mind reading is basically the attribution of mental states, such as beliefs, desires, goals, to autonomous AI systems, just to explain and predict their decisions and actions. Now, some of you might wonder why I use the word mind reading and not, for example, the intentional stance. But in the paper, I spent a whole section arguing that we should talk about mind reading and not about the intentional stance, because in the philosophical community, Dennett's theory is not very well regarded for many reasons. And basically, Stephen Stitch, who is a philosopher at Rutgers, has spent a lot of time criticizing Dennett for a lot of the presuppositions involved in the idea of the intentional stance. So that's why I prefer to write about mind reading, but explaining the whole thing would take another talk. So the talk will have the following structure. It's sort of a decision tree, an explainable decision tree. So the first question is whether humans engage in robot mind reading. The intuitive answer seems to be yes. We tend to assign beliefs and desires to all sorts of things, to abstract shapes, to animals, to our printers. So basically, it's very hard to challenge the idea that we tend to mind read all sorts of things. There are some arguments that say, well, the empirical evidence is not there yet. We might not be able, we might be using some other mechanisms to explain the behavior of robots. But for the sake of this talk, I will just assume that that we do engage in robot mind reading. Now, if we do, the next question is whether that helps with the goal of generating trust towards robots. And I will spend some time discussing this issue. It's not entirely clear that it does, but if it does, if the answer is yes, then the type of trust which is created by mind reading might present some conflicts with the goal of generating transparent AI systems. So I'll spend the second half of the talk talking about that apparent conflict between mind reading and transparency. And we should try to find out exactly what the answer is in the end. So let's start with the first question, whether robot mind reading generates trust. And here we have to find some working concept of trust. And the notion of trust has been fleshed out in many different ways in the philosophical literature. I will just use a very basic distinction between two types of trust. I don't think I need a very sophisticated, fine-grained distinction. This will do for the purpose of this talk. And it's a distinction between cognitive trust, which is trust based on rational reasons, on one's acquaintance with the person you're trusting, and especially, this is the most important part, on evidence about reliability. I'm talking about trust between people for now. On the other hand, emotional trust is a kind of trust that depends on feelings generated by your interaction with some person, and it's highly contextual and depends on social and cultural features that are not very easy to encode in a simple formula. So when you're trying to trust someone, there are these two different dimensions that are not dependent on each other. So maybe you will trust somebody cognitively, simply because you know that that person is very reliable in his or her performance, but you don't really like the person at all. Or you might attach yourself to someone you barely know, but that somehow there's some keys in his or her behavior that lead you to say, I trust this person. This person gives me some kind of good vibe or something like that. So in order to generate trust, either cognitive or emotional, you need to attribute to that person honesty, competence, and value similarity. Those three things are necessary in both of these types of trust. And to ascribe those traits to a person, you need to attribute to them some sort of intention, beliefs, desires, goals. In other words, you need to mind read what the person you trust. So far, I'm only talking about trust between people. So the question is whether robot mind reading is necessary as a condition for trust. So the question, in other words, is whether we can extrapolate the trust-building features of human relations to the field of robotics. And the most recent evidence, or the evidence that has been gathered in the last 10 years, seems to indicate that we tend to look at the behavior of robots in a way which is quite different from the way we judge human behavior. In particular, there's a very recent book by Hidalgo that says that humans are judged mostly by their intentions, while machines are judged by their outcomes. So even if a person is not so good at their job or makes mistakes, people tend to be more forgiving simply because they judge that the person has good intentions. While a failure by a machine is immediately judged very harshly, and maybe and our trust in that system goes down. Now, there's a meta study by Hancock et al. That says that performance-based factors are the largest current influence on perceived trust in human-robot interface, and that factors related to human attitudes towards robots had a very small role in trust building. So this is a meta study of lots of different studies of human-robot interaction, and it seems that the attitude that people have towards robots is not so important in generating trust. So you can this is of course very close to the idea that that we tend to apply cognitive trust towards robots, but emotional trust is a lot harder. And the problem is that there are no studies that I know of, maybe somebody here knows of more recent literature, that measure mind reading or the attitude of people towards robots in general as an independent variable in trust building. So there's no definite conclusion about the relation between mind reading and emotional trust. So the conclusion is that the jury is still out on the connection between mind reading and trust. We can't really say that promoting mind reading features in robots will enhance the trust that we have in them, because apparently performance is much more important than the idea that they behave like humans or that they have intentional states. So for the sake of this talk, just for the sake of argument, I'm going to assume that the answer to the question is yes. Robot mind reading does generate trust. And I use trust with a star, with an asterisk, because I'm talking about the specific type of trust that is promoted by mind reading. So it's the mind reading based trust that I'm going to be talking about in the rest of the talk. So let's see what that apparent conflict or possible conflict would be. Let's assume for the sake of argument that robot mind reading in fact builds trust, and also let's assume that one of the goals of robotics is that people will start trusting robots. I mean, why else would people spend so much time and effort trying to build robots, if not to make them useful to people? Now, when I talk about robots in this context, I have in mind a wide spectrum of possible systems, from the social chatbot like Replica, for example, to robots used in healthcare, to robots used in warfare, for example, in the battlefield. Some of the studies that have been done about robot trust have been done with hypothetical questions about whether you would trust a robot in a battlefield. So it's a wide spectrum of possible ways of trusting, placing your trust in robots. So if mind reading enhances trust in any dimension, then the answer to the question of whether robotics should work to enhance mind reading should be yes, they should. But the problem is that trust has a flip side. As most of you probably know, many people within the XAI community believe that in order to trust an AI system, in this case, a robot, you need to understand its actual decision-making process to make it explainable, transparent, comprehensible, and interpretable. And I won't go into the particular meanings that people have attributed to these words. That's not my purpose in this talk. All I want to point out is that there seems to be a consensus that explainability promotes trust. That it's a connection that not many people have challenged. So if robotics wants to enhance trust, then at the same time, it might also want to embrace the agenda of XAI and try to make explainable robots. Now, to be sure, there are many cases in which trust doesn't really need transparency. For example, if you're talking about a social chatbot or a robot that only has the function of providing company to a lonely person, perhaps you don't want your robot to be too transparent. In fact, some people, including Rob Boelsen, have argued that the robot's utility could be negatively affected by increased transparency. And so using mind reading features that promote mind reading just make it easier and make it make the robot fulfill its purpose, simply because it's making it look like somebody you want to talk to, somebody who's empathic, somebody who understands you, somebody you want to spend time with. But at the same time, many of these robots that provide company or that are interacting with people present some sort of risk, because some people are in a vulnerable state. They have vulnerable emotional or physical conditions. And people who are providing the robots to the patients or to the children or to whoever is using them, they have to make sure that the robot is really promoting the emotional well-being of these people, and it's not detrimental to their mental health. And the only way to do that is to understand exactly how the robot is working, how, in other words, to make it, to understand it, to explain it, to make sure that that the outcomes, the dialogue that maybe the social robot is providing is not going to make life worse for the people they are interacting with. So it seems that different stakeholders will have different demands regarding transparency. If the goal is to facilitate human-robot interaction, it would seem that transparency would get in the way of creating trust. And this is mostly the case when the goal is to create an emotional trust in the robot. But if you want to make sure that the decisions that the robot is making are warranted, that the robot is not just spilling out nonsense or learning things like the famous chatbot that went out of control on Twitter, then you need transparency. You want to obtain trust through transparency, and in that case, what you want to achieve is cognitive trust. So it seems that these are two different goals that place different demands on transparency. So the question would be, why can't we have both things? Why can't we have perhaps robots that facilitate human and robot interaction, but at the same time are more transparent about their decision-making process? Well, there is a recent trend in HRI to make something called explainable robots. But what people have in mind by the term explainable robots is not what the XAI community has in mind, because what they have in mind is to have robots that offer natural language explanations that do not purport to represent their inner states or describe their sequential decision processes. So I have a long quote here from a paper by Ehsan, who's a researcher at Georgia Tech. And they say the following: AI, they propose something called AI rationalization. And it is a process of producing an explanation for agent behavior as if a human had performed the behavior. AI rationalization is based on the observation that there are times when humans may not have full conscious access to reasons for their behavior, and consequently may not give explanations that literally reveal how a decision was made. In these situations, it is more likely that humans create plausible explanations on the spot when pressed. So these explainable robots, of course, are not transparent in the sense that the XAI community wants. They just come up with some explanation which mimics what humans would say in a similar situation. So this raises all sorts of ethical questions regarding deception. I think Tony Prescott yesterday mentioned some of the recent work on this field of robot deception. But I mean, I don't have the time to go into that aspect. So if explainable robots are not the answer, what should we do about this apparent gap between these two different goals that are present in robotics? So I want to conclude simply by pointing out some possible normative considerations that people might want to take into account. There's, I guess the main element that has to be considered to connect the two possible goals of robotics is risk, and this connects very well with what David was saying earlier. And it's the idea that robots operate in risky environments in some cases, and in some cases they just provide recreational company. So when the level of risk is very high, I guess we have a moral responsibility to make it safe by increasing robustness and transparency. That would be a reason why we should try to achieve transparency, which was one of the questions that also Carlos was pointing at the beginning. But in low risk scenarios, perhaps that moral mandate disappears, and other considerations regarding deception might be more important than the idea that perhaps the robot is completely opaque. So in sum, I would say that in high stakes situations, cognitive trust trumps emotional trust, and that transparency trumps mind reading features. But in low stake situations, I guess this inequality simply disappears. So going back to the main schema that I have here, the final answer would be, is mind reading based trust and transparency compatible goals? Are they compatible goals? So one could say yes and no. In some cases, you would have, for example, a social chatbot that provides mind-reading features and makes people trust the chatbot emotionally. But at the same time, perhaps a designer can understand perfectly what's going on behind the scenes and find an explanation for the functioning of the chatbot. But in other cases, it's simply not possible to combine both things. In some cases, you might have to choose between enhancing mind readability or enhancing transparency, and there will be no way to join the two things in one goal. So it's a yes/no situation. The answer is, well, it's complicated, I guess, which is a very common answer in this field. Thank you.
Yes, thank you, Andres, for this very clear and straightforward talk, and that you have pointed on the tension between the mind readability of robots and transparency. I think there is still enough time for one or two questions. Yes, Carlos?
Hello, I always like jumping in here. So I really like the way that you distinguish this emotional trust and cognitive trust. I think that's exactly right. I wonder though, as these robots become increasingly, human-like, I would expect us to behave vis-a-vis those robots in more and more like we behave vis-a-vis other humans, right? And I would suspect at some point, then, something. I know you don't want to talk about Dennett, but I mean, I do enjoy talking about Dennett, and so like at some point, very quickly, actually early on, I would suspect something like the intentional stance would kick in. And the intentional stance would be something like the basis of my even emotional trust here, where I'm making assumptions about the agent's beliefs, desires, and so on and so forth. I mean, I would call that a kind of transparency, right? Although, as Dennett pushes, right, it might not have very much to do with the like causal underpinnings of the behavior. It is a real pattern, so to speak, in the behavior, right? I mean, attributing beliefs, attributing intentions, desires, and so on and so forth. These are, according to Dennett at least, attributions that are realistic, right? They really have these beliefs and desires. So, I mean, in that sense, isn't that also a kind of transparency? I mean, I'm really saying that's how they work.
I mean, I would agree with you if we are talking about AI systems that actually have intentional states, but not if we're talking about an interface where the system simply speaks and says things that sound human and that reflect that pretend to have intentional states. The reason why Dennett thinks that it works so well in human-human interaction is because we have a perfect example of the connection between behavior and the intentional state, namely ourselves. So we can check that if we do something, there's an intentional state in us that corresponds to what we're doing and explains what we're doing and predicts what we're doing. But in the case of a robot that simply says, well, I was sad, well, I was trying to do this, well, I was this or that, I would still say, well, you're very well programmed to explain your behavior, but I have no idea what's really going on behind the scenes, and whether that natural language explanation that you have been programmed to give really corresponds to anything similar. There might be a black box process which has other variables and other elements going on. So that's why I wouldn't trust that. I wouldn't call that a transparency at all. No.
Okay, if I can ask a brief follow-up. I mean, but of course, Dennett is not Fodor, right? I mean, Dennett doesn't assume that the intentions attributed to a system are reflected in some causal structure underlying the behavior, right? I mean, in a sense, Dennett is a behaviorist, and he says the intentions are at the behavioral level, so to speak. So as long as the explanation given by the robot reflects these behavioral patterns, they do have those intentional states or whatever the explanation is based on. At least that's my reading of Dennett.
Sure. I mean, Dennett is a functionalist, and his the intentional stance is entirely instrumentalist. So I think he would agree with you. I don't. I think the causal underpinnings of the entire process are important.
Okay, fair enough.
That's another reason I just don't like Dennett.
Okay, thank you, Andres. This was a great talk, and we now come to the last speaker of our symposium and the last speaker of today, namely Vincent. Vincent, can you try to share your slides with us?
Okay, let's see.
And he will give a talk on how opacity threatens data privacy and XAI, right?
Yes. Okay, so now for something completely different. Yeah, this talk is a longer talk that I'm trying to squash into a shorter time, and it comes from considerations in data and big data analytics, where the problem of opacity is a little different, and I'm trying to figure out in a sort of higher level of abstraction what the problem of opacity is there, which are the problems. So this is the outline of the paper. It's a very simple paper, as you can see, and valid in its structure too. A slightly more sophisticated version of that is that I'm saying that big data is opaque, that if the big data is opaque, then we can't use standard data protection. And I conclude that we can't use standard data protection predictably. So a little bit more detail, I'll talk a little bit about big data. In fact, I will not do that today mostly. Then I'll talk about the epistemic thesis, understanding the kinds of opacity and what impact that has on our dealing with opacity and what we might do about it. I think it's important to talk about opacity, not just in terms of properties of a system, but as a relational property, so that some system or some behavior is opaque to somebody. So it could be the subject of the data, for example, it could be some technical expert, it could be the owner of the data or something else. And of course, it's also, as several of you have said, of course, not obvious what opacity really means. It could mean that we can't know that in principle, that it is difficult to know it. It could mean that it's very expensive, but it could in principle be done, but you'd have to do an enormous amount of effort, and we don't want to do that for some reason, and so on. So there are different versions of that as well, which I think should be described in a socio-technical system and not just as a technical feature of the system. And I want to suggest that there are three different types of opacity that are relevant here. And there have been all of these, no, the first two I think have been discussed, but I think smudged together with the others. So shallow opacity is what some people call algocracy. I think I find that Danaher uses that word. I find that a useful word. So sometimes you have for example, governance decisions that are made by some kind of automated system, and there's a power structure, a top-down power structure, right? So a while ago, I applied for a credit card at my Greek bank, and the credit card, and the bank came back and said no. And then I said, after they'd asked me lots of details about myself and my life, and and I asked the employee, so why is that? And the employee said, I don't know. This went to the central system. The central system said no, and that's the only thing I can tell you. I'm really surprised myself. That was it. Okay, so there's a power system there, which is problematic. The decision can't be challenged. there's nobody responsible, right? The guy in front of me, there was no point in, shouting at them or something, right? He's not responsible. So it's difficult to do anything like that. That is why this is now, there's the GDPR, which is trying to rein these things in. So it's opacity, it's shallow because it's opacity for a very particular person. So I could assume that there are people somewhere in the IT system of the bank that do understand what is going on there. But for me as the user, it is opaque. And it is a power structure that's relevant here. So the standard opacity is the kind of stuff that most of you have been talking about as far as I can tell. So essentially systems where there is some kind of structure going on, usually machine learning systems that don't have to be like that, but they're often like that, of various sorts, which have this feature, which is called the black box feature. So essentially, so it's again a little bit of a question, who is the we, right? You might, for example, be the person who might be an IT expert, but who's using the system. That's different from the person who's made the system. And as one of the speakers earlier pointed out, these systems don't fall from the skies, right? So they don't auto-generate themselves. So there's some kind of structure behind them, which I think is often forgotten in this discussion. But clearly there are cases where these systems are describing patterns that we didn't know, particularly when they're doing unsupervised learning. And in that case, we're having a classic black box problem because we can't justify the actions and find out whether they're any good. So this is, as Humphrey says, that it's epistemically opaque in the sense that we don't know the epistemically relevant elements of the process. So it's opacity even for the experts. So my suggestion is that there is perhaps a little bit more even. So let's imagine that you have access to some kind of data set. And I've had this discussion with data science people. So they say, oh, here is this data set. What is in that data set? What is the information in that data set? So this is a difficult question. We can say, in some cases anyway, which data you can't derive from that data set. But what you cannot say is which data cannot be derived from the data set if you also have an additional data set, right? So there's plenty of work that has shown these kind of interesting cases where you have a data set that seems to be anonymized, for example, but then you also have another data set which is not anonymous and has some kind of link with the first data set, and suddenly you do know, for example, which are the people in that first data set, and you can identify some of them, and then maybe you can identify more of them, and so on. So you can only say what somebody will be able to derive from the data set if you know what data they have access to and what methods they have access to. But of course, that's not something that you can say ahead of time, right? So you can only say, given these methods here and this information here, you can't derive, I don't know, the identity of these people, or you can only say that they're from this postcode area in the UK or something like this. But you can't say what might happen with new data or with new methods, right? And data science people, of course, are trying to do exactly this. They're trying to develop new methods in order to find out information from data. So which data can be derived from this data set is from this data set with this method as deductive, I'm suggesting, but which knowledge can be derived is not deductive, it's inductive. So it seems to me that there is something bigger going on here, namely that in these cases, you can't know which information the data contains. So I don't know, it might be, for example, that some feature is rare in that data. And if that is the case, then you might be able to identify a person because they have this rare feature. But you might not know that beforehand. So it seems to me that deep opacity is characteristic of big data. Of course, big data itself is not something that's sharply defined, so it is obviously there's obviously vagueness in that remark, right? So there's the bigger the data, the messier the more data sources, etc., the bigger this difficulty of opacity is. So this is the summary of that section. I think there are these three types: shallow for a particular person, black box standard type for the experts, and deep for basically anyone. And all of these, in my view, are relevant due to the need for justification of judgments. That, I think, is the major concern. We will have automated systems that make decisions or suggest decisions, and we will need to have reasons for ways to justifying these decisions. So now data protection. So here's a standard data protection system, the GDPR, really quickly, of course. And it says that the data that it talks about, so the data that it's trying to protect, is what's called personal data. That is data that is linked to a human individual. This kind of data cannot be stored without permission, of that person, except under special circumstances for public health and archiving purposes. So they have various requirements. So the third bullet point is relevant. For example, I should be able to give clear and informed consent. If I want, I should be able to get access to my data. So I should be able to go to any kind of company or public service and say, I want to see which data you have about me. Okay, and just imagine how hard that is going to be to answer. I have a right to be forgotten. So in other words, I can write something stupid in a tweet or something else, and at some point I would be able to force that this kind of thing is deleted. I have a right for explanation. That is the kind of thing that I didn't have when this story happened with the bank, and various other things like that. Okay, so these are all these rights that I supposedly have. So I think crucially here, the consent and the right to explanation, you might want to keep that in mind. So what happens in the case of this opacity there? So we need to be able to answer some questions. So for example, is there personal data in there? I mean, is it even data about people, right? It could be data about wind turbines or something completely different. Are these people identifiable? And if yes, to what extent, right? I mean, maybe they're just identifiable to some kind of probability measure, for example. You should be able, therefore, then to say whether somebody has your data. Do we have something called informed consent? So what would that even mean? If I mean, informed consent has all sorts of well-known issues. What does informed mean? But in this case, if I say, yes, I allow you to use this data for these purposes, for example, for research, how would I know what information that data actually contains? It might contain information that I didn't think of. I don't know about my sexual orientation or something else that I'd rather keep private. And can we provide an explanation? No. So it seems to me the situation is rather bad. Big data makes the threat on privacy worse and the remedy less effective, the remedy meaning the data protection systems. Okay, so that was my little talk. Here is the outline. And there are some technical things where people try to make things not quite as bad, but it seems to me that there is a fairly serious difficulty around here that we should pay some attention to. Thank you.
Thank you. That's very helpful and nice to, I mean, I think this notion of deep opacity is new and really cool. Does anybody have any questions? If so, just ask. If not, or also write it into the chat. It's been a long symposium, but we can have a couple of questions.
If I may, in grand tradition, having seen modus ponens, I want to have modus tollens. So you say we have opacity entails there's no data protection. Sorry, implicates, my logic lecturers would be very happy with me. But sometimes we can have data protection. They're incomplete, but maybe we can run this modus ponens the other way and have something like a graduation of opacity, such that the kind of things that we have at least incomplete data protections for could be, that could indicate the extent to which the data is and isn't opaque. Do you think there's any chance for that? So we can have something like a scale of opacity? Yes,
that's a nice idea. I hadn't thought of this. Yes, of course, I think that could work. So if you keep the conditional the way it was, right? So if we have opacity, we don't have data protection, and then you say, but here in this area we do have data protection, therefore we do not have opacity. That sounds good. It sounds good also to me because it stresses the point that opacity is a feature of a socio-technical system, right? So it is in this area you can say, now here we have data protection. That means that we have a system that the people whose data is at stake understand, can consent to, can control, and so on. And in this area that might work. And I think you're right also to point out that my pessimistic conclusion might have been stated a little bit too broadly, right? So obviously there are areas where data protection is possible, right? And so you should say yes, and therefore there are areas where opacity doesn't seem to be the issue. So that is, yes, I think that's a nice point, and consistent with what I said too.
We have a question from Katie in the chat. She asks, thank you for the talk. What do you think about the differential privacy and the claim that it can offer privacy without transparency?
Yes, very good. That is a little section I have at the end of the talk. So caveat. This is a technical discussion which I'm trying to grasp. Okay, I'm not sure that I do. And I understand that some people think that they can prove something there, which is good. If you can prove it, then I should take it from the experts that has been proven. So differential privacy relies on the idea that you do something to the data collection process in such a way that private data is never even generated. You get everything you want, for example, some statistical correlation that you're after, but you don't have any private data to start with. So it's completely different from the view. Okay, you know that I'm just explaining. It's completely different from the view that you anonymize the data afterwards, which, as we know, has all sorts of risks. Apart from the fact that you had the non-anonymized data somewhere, it's also risky because people can find smart tricks to go backwards. So if differential privacy really works, then there is no way, or you can go backwards as much as you like, but there isn't any private data to start with. So it seems to me that that is a very, very useful type of technique. I understand from conversations with people in statistics that there are other ways of doing this, aggregating data, where you can, so to speak, where you do start with private data, you aggregate it in a way that is useful for you, and you dump the private data completely, where they say also they can prove that you can't go down from there anymore. And it seems to me that it makes a lot of sense for many, many users to use something like these differential privacy systems, because the excuse, I would say, I mean, the reason people say, but I would call it an excuse for collecting the private data often is that people are interested in some statistical correlation. That could be the way you're using your smartphone, or I don't know, how your diet is related to your diseases or something like this, right? But you don't actually need to know how Vincent is using his smartphone in order to do that. That is completely irrelevant to your research, right? You just need to know how people in general use that statistically. So I think that is a very good path which should be used a lot more often. And I pray that the people who say that it can be proven that that works fine are right about it. because I can really only take that on trust. But it seems to be that there are some mathematical results there that one can trust. And some of these I've tried to grasp, and they seem plausible to me. So yes, I think that is a really interesting line.
I think David has a question.
Yeah, thanks. I was just going to say, first of all, it's a really interesting talk, a bit of a different direction, as you said, from other stuff today. Kind of building on Katie's point, just asking about technical, maybe, I don't want to say solutions, complications to this problem. Another thing I've heard people talking about recently, I don't know if it's nearly as far along as differential privacy, is this idea of synthetic data to retain privacy. So, you know, if you had like a, say you had a very reliable generative model, like these GANs they use for like image data. Sometimes you've probably seen these, you know, fake portraits or whatever that you can generate that look very real. You could generate data that looked very real and retained, as you say, some of the population level structure of correlations or whatever, the covariance of the full feature space. You could do that without, in principle, giving up any private information about any individual, because every single data point in that data set is synthetic. Is that a possible workaround to these issues?
That last bit is, of course, problematic, because you do need to make sure that that synthetic data has the features that you want, right? So you have to somehow have other data and then say, okay, what I really care about here is the correlation between, I don't know, age and hair loss or something, right? And you say, okay, good. So I take all these guys and I look at what and I invent these synthetic data points, these new people. So yeah, there I think I would be more cautious about the correlation between the original data and the data that you're generating, what that might produce. And also notice it could, of course, be sometimes it could be a problem if you have synthetic data that is personal data about populations of people. So if there is a population that is, for example, suppressed in your society or something like that, then that could be an additional problem that is generated in this area. But generally speaking, there is synthetic data, and there is also, but of course that's a problem in this area too, is data donation. Right. So when people say, okay, yes, I'm happy with my data to be used, for example, for health research, right? A lot of people who have some kind of health conditions would say that, right? You know, if you can use my data to help other people who have my condition in the future, sure, go ahead, you know, use it. And that's exactly the point where you try to say, okay, good, let's try to do that. And let's do it in such a way that you make sure that the individual data is protected. And there the problem is, you have to, so to speak, know what's relevant before you start, right? Because if you throw away some data, I don't know, about some feature of that person, and then later on you discover that, oh, perhaps that might have been a causally relevant factor in the discussion, then you're in trouble, right? So
sorry, if I could just quickly follow up to make this kind of concrete. Imagine a circumstance where you are, it's not necessarily a clinical study, it could be something almost more biomolecular, right? So like GWAS data sets, these big genetic data sets, UK Biobank has millions, one of the biggest collections in the world. And in principle, we know what the range of possible features are, because there's 3.2 billion base pairs, and that's just the space. Everyone's going to have something along that. And I don't think we're quite far along enough yet to do this reliably, but imagine we got to a point where we understood the covariance structure along these base pairs well enough that we could sample possible humans that are identical to no existing humans, but are plausible given, you know, what we know about the space or something. And then we could study that synthetic data set to show whatever, some property or connection between a disease or a treatment regime or something. That's sort of the situation I have in mind, where the feature space is kind of predefined for you.
Yes, I think that is fine. So what you would do there would be that you go away from the individual cases to a theoretical understanding of it and say, these are the relevant features here. This is how these things hang together. And as you say, the space is finite. And so I can say, I can generate new data along those lines. So that kind of thing seems plausible to me. So you would start with personal data, but then the next step, the synthetic data, would be quite independent from that. So in that case, that seems to be a good idea, yes. Again, there's going to be an interesting social question when people will feel the need to do that, right? And actually go through the pains of doing that kind of activity. And for example, generate new data. Well, as you said, there's already a huge database with actual data. So why bother?
I would say it's 8 minutes before the hour. And it's been a long symposium, and we have a plenary talk still by Peter Robinson coming up. I would suggest to end the symposium here. Before we all go away, I want to say thank you to all speakers, of course, everyone who submitted, the reviewers who are mostly not here.
Thank you.
And of course to the audience who is here listening and asking great questions. And thank you very much to everything and everyone. So,
okay. Can I just add to that?
Organizing.
One more quick announcement.
Sorry, can I just add to that? On behalf of AISB, many thanks to the organizers, all the speakers of the symposium, and the participants. It's been great, and we hope to see you again next year.
Yeah, thank you too.
Thank you.
Bye-bye, everyone. Thanks a lot.
Bye-bye.